What if the universe had a speed limit, and breaking it could unravel the very fabric of reality? Imagine a world where light doesn't just illuminate the darkness. It holds the secrets to time, space, and the mysteries of existence itself. Welcome to a journey through the cosmos, where we explore 50 mind-blowing facts about the universe's most extreme speeds of light. From the mind-bending theories of relativity to the cosmic dance of black holes and quasars, this isn't just about how fast light travels. It's about how light shapes everything we know about the universe. Why does this matter? Because understanding the speed of light isn't just for scientists, it's a window into the very nature of reality, a key to unlocking the secrets of the cosmos. So, buckle up and get ready to dive into a world where light bends time, warps space, and reveals the universe's most astonishing truths. By the end of this video, you'll see the universe in a whole new light, literally. Let's begin. Now, let's dive into the very first fact that sets the stage for everything we know about light and the universe. The speed of light in a vacuum is a staggering 299,792,458 meters per second. That's right, this number isn't just a random figure. It's a universal constant, a speed limit that nothing in the cosmos can surpass. Think of it as the ultimate cosmic speed limit, a rule written into the very fabric of reality. This speed isn't just fast, it's the foundation of Einstein's theory of relativity, which revolutionized our understanding of space and time. According to Einstein, the speed of light is the same for all observers, no matter how fast they're moving. This idea might sound simple, but it has mind-blowing implications. It means that time and space aren't fixed, they stretch and warp depending on how fast you're traveling. The speed of light isn't just a number, it's a key that unlocks the mysteries of the universe, from black holes to the Big Bang. So, the next time you see a beam of light, remember, it's not just illuminating the darkness, it's holding the secrets of existence itself. Now, let's take a step back and think about just how vast the universe really is. To measure these unimaginable distances, scientists use the speed of light as their cosmic ruler. Enter the concept of the light year, a unit that might sound like it measures time, but actually measures distance. 1 light year is the distance light travels in 1 year, which comes out to about 9.46 trillion kilometers. That's 9,460 billion kilometers. To put it another way, if you could travel at the speed of light, it would take you an entire year to cover that distance. But here's the kicker: even at this incredible speed, light from the nearest star to our solar system, Proxima Centauri, takes over 4 years to reach us. And that's just our cosmic backyard. When we look at galaxies millions or even billions of light years away, we're essentially peering into the past, seeing them as they were when the light first began its journey. This is why the speed of light is so crucial. It not only helps us measure the scale of the universe, but also allows us to explore its history. Without this universal speed limit, we'd have no way to grasp the true enormity of space or the stories it holds. So the next time you hear the term light year, remember, it's not just a measure of distance, it's a window into the cosmos itself. Now, let's shift our focus to something that might seem counterintuitive at first. Light doesn't always travel at its maximum speed. While we often think of light as zipping through space at its universal speed limit of 299,792,458 meters per second, it actually slows down when it passes through different materials. This phenomenon is known as refraction, and it's the reason why a straw in a glass of water looks bent or why a rainbow forms after a rainstorm. When light enters a medium like water, glass, or even air, it interacts with the atoms and molecules in that material. These interactions cause the light waves to slow down, bending as they pass from one medium to another. The degree to which light slows down depends on the material's optical density, which is measured by something called the refractive index. For example, light travels about 25% slower in water than in a vacuum, and even slower in glass. This slowdown isn't just a neat trick of nature. It's a fundamental principle that underpins technologies like lenses, fiber optics, and even your eyeglasses. So the next time you see light bending or slowing down, remember, it's not breaking the rules of physics, it's just playing by them in a whole new way. Now, let's take a step back from the natural world and look at what humanity has achieved in the realm of speed. While light travels at an astonishing 299,792,458 meters per second in a vacuum, human-made objects are still far from matching that pace. The fastest human-made object to date is the Parker Solar Probe, a spacecraft designed to study the Sun up close. At its peak, the Parker Solar Probe reaches speeds of around 692,000 kilometers per hour. That's incredibly fast enough to travel from New York to Tokyo in under a minute. But here's the catch. Even at that blistering speed, the Parker Solar Probe is only moving at about 0.064% of the speed of light. To put it another way, if light were a race car speeding down a highway, the Parker Solar Probe would be a bicycle pedaling in the same direction. So why is it so hard for us to reach even a fraction of light speed? The answer lies in the immense amount of energy required. According to Einstein's theory of relativity, as an object approaches the speed of light, its mass increases exponentially. This means that the faster you go, the more energy you need to keep accelerating. To reach even 10% of the speed of light, we'd need an energy source far beyond anything we currently have. Chemical rockets, like the ones used to launch the Parker Solar Probe, simply don't have the power to get us there. Scientists are exploring alternative propulsion methods such as ion drives, nuclear propulsion, and even light sails, but these technologies are still in their infancy. The challenges don't stop at energy requirements, though. Traveling at such extreme speeds also poses risks to both the spacecraft and any potential crew. Tiny particles in space, like dust or micrometeoroids, could cause catastrophic damage when colliding with a vessel moving at near light speeds. And then there's the issue of time dilation, a phenomenon we'll explore in more detail later, where time slows down for objects traveling close to the speed of light. While this might sound like science fiction, it's a very real consequence of relativity that would need to be accounted for in any future high-speed missions. Despite these challenges, the pursuit of faster speeds continues to drive innovation in space exploration. The Parker Solar Probe is just one example of how far we've come, and it serves as a reminder of how much further we have to go. As we push the boundaries of what's possible, we're not just chasing speed, we're unlocking new ways to explore the universe and understand our place within it. So, while we may not be breaking the light barrier anytime soon, every step we take brings us closer to the stars. Now, let's shift gears and dive into a concept that has captured the imagination of science fiction fans and physicists alike: warp speed. You've probably heard of it in shows like Star Trek, where starships zip across the galaxy faster than the speed of light. But is warp speed just a fantasy, or could it have a basis in real science? Surprisingly, the answer lies somewhere in between. The idea of warp speed revolves around bending the fabric of spacetime itself. Instead of trying to move through space at impossible speeds, a warp drive would theoretically compress spacetime in front of a spacecraft and expand it behind, effectively creating a warp bubble. Inside this bubble, the ship wouldn't actually be moving faster than light. It would be riding a wave of distorted spacetime. This clever workaround sidesteps Einstein's rule that nothing can travel faster than light in a vacuum because the ship itself isn't breaking the speed limit. It's the spacetime around it that's doing the heavy lifting. This concept isn't just science fiction. In the 1990s, physicist Miguel Alcubierre proposed a theoretical model for a warp drive, now known as the Alcubierre drive. His equations showed that, in theory, such a drive could work without violating the laws of physics. However, there's a catch. The Alcubierre drive would require something called exotic matter, a type of matter with negative energy density to create the warp bubble. The problem, exotic matter has never been observed in nature, and we have no idea how to produce it. Even if we could find or create exotic matter, the energy requirements for a warp drive would be astronomical. Some estimates suggest it would take the energy equivalent of several Jupiter-sized masses just to power a small warp bubble. And then there's the issue of controlling the warp bubble itself. If not managed perfectly, the bubble could collapse, releasing massive amounts of energy that could destroy the ship or, worse, create a black hole. Despite these challenges, the concept of warp speed continues to inspire scientists and engineers. While it may not be a reality anytime soon, the idea pushes us to think beyond conventional propulsion methods and explore the boundaries of what's possible. Who knows, one day warp drives might not just be the stuff of science fiction, they could be the key to unlocking the stars. So, while we're still far from bending space-time to our will, the dream of warp speed reminds us that the universe is full of possibilities waiting to be discovered. And speaking of possibilities, let's take a closer look at what happens to time itself when you approach the speed of light, a phenomenon that's as mind-bending as it is real. Now, let's take a step into one of the most fascinating consequences of traveling near the speed of light, time dilation. This is where things get truly mind-bending, thanks to Einstein's theory of relativity. Imagine this time isn't as constant as it seems. In fact, it can stretch and slow down depending on how fast you're moving, and the closer you get to the speed of light, the more dramatic this effect becomes. To understand this, let's break down the famous twin paradox. Picture two identical twins. One stays on Earth, living a normal life, while the other boards a spacecraft and zooms off into space at a significant fraction of the speed of light. After a few years, the traveling twin returns to Earth, but here's the twist. The twin who stayed on Earth has aged much more than the one who traveled. For the spacefaring twin, time passed more slowly. This isn't science fiction, it's a real prediction of Einstein's theory of relativity. Why does this happen? It all comes down to the relationship between speed and time. As an object moves faster, time for that object slows down relative to someone who isn't moving as quickly. This effect is called time dilation, and it's been proven experimentally. For example, atomic clocks on fast-moving airplanes or satellites tick slightly slower than those on the ground. The difference is tiny, but it's there. Now, imagine that difference amplified to near light speeds. Time could slow down dramatically. But here's the kicker. The traveling twin wouldn't notice anything unusual during their journey. To them, time would feel normal. It's only when they return and compare their experiences that the difference becomes apparent. This paradox highlights just how strange and counterintuitive the universe can be when you start pushing the limits of speed. So, what does this mean for us? Well, if we ever figure out how to travel at near light speeds, time dilation could become a real factor in space exploration. A journey that takes decades for people on Earth might feel like just a few years for the astronauts on board. It's a wild concept, but it's grounded in solid science. And with that, we've only scratched the surface of how time and speed intertwine in the cosmos. Next, let's explore what happens when light itself can't escape the pull of a black hole, a place where time and space are twisted beyond recognition. Now, let's venture into one of the most extreme environments in the universe: black holes. These cosmic giants are so powerful that they warp the very fabric of space-time itself. And when it comes to light, black holes are the ultimate trap. Not even light, the fastest thing in the universe, can escape their immense gravitational pull once it crosses a certain point. This point of no return is known as the event horizon. To understand why light can't escape, let's break it down. Gravity, as we know, is the force that pulls objects toward each other. But in the case of a black hole, gravity is so intense that it bends space-time to an extreme degree. Imagine spacetime as a stretched rubber sheet. A massive object like a star creates a dip in the sheet, but a black hole creates a bottomless pit. Anything that gets too close, including light, gets pulled in and can't climb back out. The event horizon is the boundary around a black hole where the escape velocity, the speed needed to break free from gravity, equals the speed of light. Since nothing can travel faster than light, anything that crosses this boundary is doomed to fall into the black hole. It's like a one-way door. Once you step through, there's no turning back. But here's where it gets even more fascinating. The event horizon isn't just a physical barrier, it's also a point where time and space behave in bizarre ways. For someone watching from a safe distance, an object falling into a black hole would appear to slow down as it approaches the event horizon, eventually seeming to freeze in place. This is because the intense gravity stretches time itself, a phenomenon known as gravitational time dilation. Meanwhile, for the object falling in, time would feel normal, but the pull of the black hole would be unstoppable. Black holes also have a profound effect on light that doesn't cross the event horizon. Light passing near a black hole gets bent and distorted, a process called gravitational lensing. This can create strange visual effects like multiple images of the same object or even a ring of light around the black hole, known as an Einstein ring. These distortions are a direct result of how black holes warp spacetime. So, what does this mean for our understanding of the universe? Black holes are like cosmic laboratories, pushing the laws of physics to their limits. They challenge our understanding of gravity, light, and even the nature of reality itself. And while they might seem like destructive forces, they also play a crucial role in shaping galaxies and the cosmos as a whole. With that, we've explored how black holes bend the rules of light and spacetime. Next, we'll journey back in time to the early universe, where the speed of light might have been very different, and how that could explain some of the biggest mysteries of the cosmos. Now let's take a step back in time, way back to the very beginnings of the universe. What if I told you that the speed of light, that constant we rely on to measure the cosmos, might not have always been the same? In the early universe, some scientists believed that light could have traveled at a different speed, and this idea might hold the key to solving some of the biggest mysteries in cosmology. One of the most intriguing theories is called variable speed of light, or VSL. This idea suggests that in the first moments after the Big Bang, light may have moved faster than it does today. Why does this matter? Well, it could help explain a phenomenon known as cosmic inflation. Inflation is the rapid expansion of the universe that occurred just fractions of a second after the Big Bang. It's what smoothed out the universe, making it look so uniform on large scales. But here's the puzzle. If light traveled at its current speed, there wouldn't have been enough time for distant regions of the universe to communicate and reach the same temperature. So how did they end up so similar? This is where the idea of a faster speed of light comes in. If light moved quicker in the early universe, it could have allowed these regions to interact and balance out, solving the so-called horizon problem. It's like imagining a group of people spread out across a vast field. If they could run faster, they'd have an easier time meeting up and sharing information. Similarly, a faster speed of light would have allowed the universe to even out much more quickly. But how could the speed of light change? Some theories propose that the laws of physics themselves were different in the early universe. For example, the strength of fundamental forces or the properties of spacetime might have varied, allowing light to travel faster. This doesn't mean the speed of light was random. It would have been governed by the conditions of the early cosmos, which were far more extreme than anything we see today. Of course, this is still a highly debated topic. The standard model of cosmology assumes the speed of light has always been constant, and it's done a pretty good job of explaining what we observe. But the variable speed of light theory offers an alternative perspective, one that could help us understand why the universe looks the way it does. It's a reminder that even the most fundamental constants we take for granted might have a more complex history than we realize. So, what does this mean for our understanding of the universe? If the speed of light was different in the past, it could reshape our theories about the Big Bang, inflation, and even the nature of space-time itself. It's a fascinating idea that challenges us to rethink what we know, or think we know about the cosmos. With that, we've explored how the speed of light might have played a role in the early universe. Next, we'll dive into another mind-bending concept, quantum entanglement, where particles seem to communicate instantaneously, defying the speed of light as we understand it. Now, let's shift our focus to one of the most baffling phenomena in physics, quantum entanglement. Imagine two particles like twins born together and then separated by vast distances. No matter how far apart they are, these particles remain mysteriously connected. If you change the state of one, say, by measuring its spin, the other instantly changes too, as if they're communicating faster than the speed of light. This is quantum entanglement, and it's a concept that seems to defy everything we know about the universe's speed limits. At first glance, this might sound like science fiction, but it's very real. Scientists have conducted countless experiments confirming that entangled particles can influence each other instantaneously, even when separated by thousands of kilometers. This phenomenon has been called spooky action at a distance by none other than Albert Einstein, who was deeply skeptical about it. He believed that nothing could travel faster than light, so the idea of instantaneous communication between particles seemed impossible. Yet, experiments have consistently shown that entanglement is real, and it's one of the cornerstones of quantum mechanics. So, how does this challenge our understanding of the speed of light? Well, according to Einstein's theory of relativity, nothing can travel faster than light. It's the ultimate speed limit of the universe, but quantum entanglement appears to break this rule. When two entangled particles interact, their connection seems to happen instantly without any delay. This raises a big question. Are these particles somehow sending information faster than light, or is something else going on? The answer lies in the strange nature of quantum mechanics. Unlike classical physics, where objects have definite properties, quantum particles exist in a state of probability until they're measured. When you measure one entangled particle, its state becomes definite, and its partner's state instantly becomes definite too, no matter how far apart they are. But here's the catch: this doesn't mean information is actually traveling between them. Instead, it's as if the particles are part of a single, unified system, and their states are linked in a way that transcends space and time. This doesn't violate the speed of light because no usable information is being transmitted. You can't use entanglement to send a message faster than light, for example. The changes in the particle states are random and can't be controlled, so they don't allow for faster than light communication. Still, the fact that entangled particles can influence each other instantaneously challenges our classical understanding of how the universe works. It suggests that there's a deeper layer of reality, one where the rules of space and time might not apply in the way we're used to. Quantum entanglement has practical applications too. It's the foundation of quantum computing and quantum cryptography, technologies that could revolutionize how we process information and secure communications. But it also leaves us with profound questions about the nature of reality. Does the universe operate on principles we're only beginning to understand? And if so, what does that mean for our understanding of light speed and the fabric of space-time? As we wrap up this exploration of quantum entanglement, we're left with more questions than answers. But that's the beauty of science. It constantly pushes us to rethink what we know. Next, we'll dive into another fascinating experiment that once seemed to challenge the speed of light. The opera experiment, where neutrinos appeared to travel faster than light. What really happened, and how did scientists solve the mystery? Let's find out. Now, let's turn our attention to a moment in science that sent shockwaves through the physics community, the Opera experiment of 2011. This experiment made headlines when it suggested that neutrinos, tiny, nearly massless particles, might be breaking the universe's ultimate speed limit by traveling faster than light. At the time, this claim was nothing short of revolutionary, and it sparked intense debate and excitement. Could it be that neutrinos had found a way to outpace light itself? The Opera experiment, conducted deep underground in Italy, involved firing a beam of neutrinos from CERN in Switzerland to a detector over 700 kilometers away. Scientists measured the time it took for the neutrinos to make this journey and, to their astonishment, found that they arrived 60 nanoseconds faster than light would have. That's 60 billionths of a second, a tiny difference, but one that, if true, would have upended our understanding of physics. The implications were staggering. If neutrinos could travel faster than light, it would mean that Einstein's theory of relativity, which has been the foundation of modern physics for over a century, might need serious revision. The scientific community was both fascinated and skeptical. Could this really be happening, or was there a mistake in the experiment? As it turns out, the answer was the latter. After months of intense scrutiny and follow-up experiments, scientists discovered that the faster-than-light result was due to a combination of technical errors. One of the key issues was a faulty fiber optic cable that caused a delay in the timing measurements. Another problem was an improperly calibrated clock. When these errors were corrected, the neutrinos were found to be traveling at speeds consistent with the speed of light, not exceeding it. While the initial excitement over faster-than-light neutrinos turned out to be a false alarm, the Opera experiment still holds an important place in the history of science. It's a reminder of how rigorous the scientific process is. Even when a result seems groundbreaking, it must be tested, retested, and verified before it can be accepted. The Opera experiment also highlighted the incredible precision required in modern physics, where even the tiniest error can lead to massive misunderstandings. So, what does this mean for our understanding of the speed of light? It reaffirms that light speed remains the universe's ultimate speed limit, at least as far as we know. Neutrinos, despite their ghostly ability to pass through matter almost undisturbed, still obey the same cosmic rules as everything else. And while the Opera experiment didn't rewrite the laws of physics, it did remind us of the importance of curiosity, skepticism, and the relentless pursuit of truth in science. As we move forward, let's explore another fascinating aspect of light speed: gravitational waves. These ripples in space-time, predicted by Einstein and detected for the first time in 2015, also travel at the speed of light. How do they work, and what do they tell us about the universe? Let's find out. Now, let's dive into one of the most groundbreaking discoveries in modern physics: gravitational waves. These ripples in space-time, first predicted by Albert Einstein over a century ago, were finally detected in 2015, and they travel at the speed of light. But what exactly are gravitational waves, and why are they so important to our understanding of the universe? Gravitational waves are created by some of the most violent and energetic events in the cosmos, like the collision of black holes or the explosion of massive stars. When these events occur, they send out waves that distort the fabric of spacetime itself, much like ripples spreading across the surface of a pond. And just like light, these waves travel at the ultimate cosmic speed limit: 299,792,458 meters per second. The detection of gravitational waves was a monumental achievement. Using incredibly sensitive instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, scientists were able to measure these tiny distortions in spacetime, some of which are smaller than the width of an atom. This discovery confirmed Einstein's prediction and opened up an entirely new way of observing the universe. Before gravitational waves, our view of the cosmos was limited to what we could see with light, radio waves, and other forms of electromagnetic radiation. But now we can listen to the universe through these ripples in space-time, giving us a whole new perspective. One of the most exciting aspects of gravitational waves is that they allow us to study events that are completely invisible to traditional telescopes. For example, when two black holes collide, they don't emit any light, but they do produce powerful gravitational waves. By detecting these waves, scientists can learn about the properties of black holes, such as their mass, spin, and distance from Earth. This has already led to new insights into how black holes form and evolve. Gravitational waves also provide a unique way to test Einstein's theory of general relativity. So far, every observation of gravitational waves has matched the predictions of relativity, further confirming its accuracy. But as we continue to detect more of these waves, there's always the possibility that we might find something unexpected, something that could challenge our current understanding of physics. The speed at which gravitational waves travel is another fascinating aspect. Because they move at the speed of light, they allow us to observe cosmic events almost in real time. For example, when two neutron stars collided in 2017, gravitational waves from the event reached Earth just moments before the light from the explosion did. This gave astronomers a rare opportunity to study the same event using both gravitational waves and traditional telescopes, leading to a wealth of new discoveries. In many ways, gravitational waves have revolutionized our understanding of the universe. They've given us a new tool to explore the cosmos, one that complements what we can learn from light and other forms of radiation. And as our detectors become even more sensitive, we'll be able to observe even more distant and faint events, uncovering secrets of the universe that were previously hidden from us. So, what's next for gravitational wave astronomy? With new observatories being planned and built around the world, we're on the brink of an even deeper understanding of the universe. From probing the nature of dark matter to uncovering the mysteries of the early universe, gravitational waves promise to keep revealing the cosmos in ways we've never imagined. And as we continue to explore, one thing is certain: the speed of light remains at the heart of it all, guiding our journey through the mysteries of space-time. Now let's shift our focus to one of the most mind-bending consequences of the speed of light: cosmic expansion. You might think that nothing can outpace light, but when it comes to the vast scale of the universe, things get a little more complicated. Thanks to the expansion of space itself, distant galaxies can appear to be moving away from us faster than the speed of light. How is that possible? Let's break it down. The key here is understanding that it's not the galaxies themselves moving through space at such incredible speeds. Instead, it's the space between us and those galaxies that's stretching. Imagine the universe like a balloon being inflated. If you draw dots on the surface of the balloon as it expands, the dots move away from each other. Now, if the balloon expands fast enough, two dots could move apart faster than the speed of light, even though neither dot is actually moving through the balloon's surface. That's essentially what's happening with distant galaxies. This phenomenon is a direct result of something called the Hubble constant, which measures how fast the universe is expanding. The farther away a galaxy is from us, the faster it appears to be receding. At a certain distance, known as the Hubble radius, galaxies are moving away so quickly that their light can never reach us. This doesn't violate Einstein's theory of relativity because it's not the galaxies moving through space, it's space itself expanding. What's truly fascinating is that this expansion is accelerating, driven by a mysterious force known as dark energy. As the universe continues to expand, more and more galaxies will cross that Hubble radius, disappearing from our observable universe forever. It's a sobering thought. The universe is not only vast but also growing at a rate that ensures some parts of it will remain forever out of reach. This cosmic expansion also has implications for the speed of light. While light itself still travels at its constant speed, the stretching of space means that the distance it has to cover increases over time. This is why light from the most distant galaxies takes billions of years to reach us, and why some of that light will never arrive at all. So, while the speed of light remains the ultimate speed limit for anything moving through space, the expansion of the universe shows us that space itself plays by different rules. It's a reminder that the cosmos is full of surprises, constantly challenging our understanding of the laws that govern it. And as we continue to explore, the speed of light remains our guide, helping us unravel the mysteries of an ever-expanding universe. Now, let's turn our attention to one of the most spectacular displays of cosmic speed, relativistic jets. These are incredibly powerful beams of energy that shoot out from black holes and neutron stars, and they're some of the fastest things in the universe. In fact, these jets can travel at speeds so close to the speed of light that they challenge our understanding of physics. Relativistic jets are born in some of the most extreme environments imaginable. When matter spirals into a black hole or gets pulled toward a neutron star, it doesn't just disappear quietly. Instead, it gets heated to unimaginable temperatures and accelerated to nearly the speed of light. Some of this material gets funneled into narrow jets that blast outward from the poles of these cosmic powerhouses. These jets can stretch for thousands, even millions of light years, far beyond the galaxies they originate from. What makes these jets truly remarkable is their speed. While they don't quite reach the speed of light, they come incredibly close, often traveling at more than 99% of light speed. At these velocities, the effects of Einstein's theory of relativity become incredibly pronounced. Time slows down for the particles in these jets, and their energy increases dramatically. This is why relativistic jets emit such intense radiation, from radio waves to gamma rays, making them some of the brightest objects in the universe. But how do these jets form in the first place? It all comes down to the extreme gravitational and magnetic fields around black holes and neutron stars. As matter falls toward these objects, it gets twisted and compressed, creating a swirling disk of superheated gas. Magnetic fields within this disk channel some of the material into tightly focused jets, which are then launched into space at nearly the speed of light. It's like a cosmic particle accelerator on a scale we can barely comprehend. The energy released by these jets is staggering. In some cases, they can outshine entire galaxies despite being much smaller in size. This makes them a key area of study for astronomers, as they provide insights into the behavior of matter under the most extreme conditions. By observing relativistic jets, scientists can learn more about the nature of black holes, neutron stars, and the fundamental laws of physics. So, while the speed of light remains the ultimate speed limit, relativistic jets show us just how close nature can get to breaking the rules. They're a testament to the incredible forces at work in the universe, and a reminder that even the most extreme phenomena are governed by the same laws that shape our everyday reality. As we continue to study these jets, they offer a window into the mysteries of the cosmos, pushing the boundaries of what we thought was possible. Now, let's shift our focus to one of the most explosive and energetic phenomena in the cosmos, gamma-ray bursts. These are the universe's most powerful explosions, releasing more energy in just a few seconds than our sun will emit over its entire lifetime. And here's the fascinating part: this energy travels across the universe at the speed of light, carrying with it clues about some of the most extreme events in existence. Gamma-ray bursts are thought to occur during some of the most dramatic moments in the life cycle of massive stars. When a star many times more massive than our sun exhausts its fuel, it doesn't just fade away, it collapses under its own gravity, triggering a supernova. In some cases, this collapse leads to the formation of a black hole, and as matter spirals into this newly formed black hole, it releases two incredibly powerful jets of energy. These jets, traveling at nearly the speed of light, produce the gamma-ray bursts we observe. But gamma-ray bursts aren't just about the birth of black holes. They can also occur when two neutron stars collide, merging into a single, more massive object. This collision sends ripples through space-time, known as gravitational waves, and produces a burst of gamma rays that travels across the universe at light speed. These events are so bright that they can be detected from billions of light years away, making them some of the most distant and ancient phenomena we've ever observed. What's truly mind-blowing is how quickly these bursts happen. A typical gamma ray burst lasts only a few seconds, but in that short time, it outshines entire galaxies. The light from these bursts travels across vast cosmic distances, sometimes taking billions of years to reach us. When we detect a gamma ray burst, we're essentially looking back in time, witnessing an event that occurred when the universe was much younger. The speed of light plays a crucial role in how we study these bursts. Because light travels at a constant speed, the time it takes for the gamma rays to reach us tells us how far away the burst occurred. This allows astronomers to map the locations of these events and study the conditions of the early universe. Additionally, the afterglow of a gamma ray burst, which can be observed in other wavelengths like X-rays and visible light, provides further insights into the nature of these cataclysmic events. Gamma ray bursts are not just cosmic fireworks, they're also windows into the most extreme environments in the universe. By studying them, scientists can learn about the behavior of matter and energy under conditions that are impossible to recreate on Earth. They also help us understand the life cycles of massive stars, the formation of black holes, and the dynamics of neutron star collisions. So while gamma ray bursts are fleeting, their impact is anything but. They remind us that even the most distant and ancient events in the universe are connected to us through the speed of light, carrying stories of cosmic violence and transformation across the vast expanse of space and time. As we continue to observe these bursts, they challenge our understanding of the universe and inspire us to explore its deepest mysteries. Now, let's turn our attention to another fascinating cosmic phenomenon: pulsars. These rapidly spinning neutron stars are like the universe's natural lighthouses, emitting beams of light that sweep across space at incredible speeds. Pulsars are born from the remnants of massive stars that have gone supernova, leaving behind an incredibly dense core. This core, spinning hundreds of times per second, emits intense beams of radiation from its magnetic poles. As the pulsar rotates, these beams sweep through space, and if they happen to point toward Earth, we detect them as regular pulses of light, hence the name pulsar. What's truly remarkable is the speed at which these beams travel. The light emitted by pulsars moves at the speed of light, of course, but it's the rotation of the pulsar itself that creates the illusion of a cosmic lighthouse. Imagine a beam of light spinning so fast that it completes a full rotation in just milliseconds. This rapid spinning, combined with the speed of light, allows pulsars to produce some of the most precise and predictable signals in the universe. In fact, some pulsars are so regular that their pulses can be used as cosmic clocks, helping astronomers measure time and distance with incredible accuracy. Pulsars also provide a unique window into the behavior of matter under extreme conditions. The density of a neutron star is so immense that a single teaspoon of its material would weigh billions of tons on Earth. This extreme environment, combined with the pulsar's rapid rotation and powerful magnetic fields, creates conditions that are impossible to replicate in any laboratory. By studying the light emitted by pulsars, scientists can learn about the physics of super-dense matter, the nature of magnetic fields, and even the fabric of space-time itself. The speed of light plays a crucial role in how we observe and interpret pulsars. Because light travels at a constant speed, the timing of the pulses we detect tells us not only about the pulsar's rotation, but also about its distance from Earth. This allows astronomers to map the locations of pulsars across the galaxy and use them as markers to study the structure and dynamics of the Milky Way. Additionally, the precise nature of pulsar signals has made them invaluable tools for testing theories of gravity, including Einstein's general theory of relativity. Pulsars are more than just cosmic curiosities, they're also key players in some of the most exciting discoveries in modern astronomy. For example, the first exoplanets ever discovered were found orbiting a pulsar, and pulsars have been used to detect gravitational waves, ripples in spacetime caused by cataclysmic events like the collision of black holes. These discoveries highlight the incredible versatility of pulsars as tools for exploring the universe. So, while pulsars may seem like distant, exotic objects, they're deeply connected to our understanding of the cosmos. Their beams of light, traveling at the speed of light, carry with them a wealth of information about the universe's most extreme environments. As we continue to study these cosmic lighthouses, they illuminate not just the darkness of space, but also the mysteries of physics, gravity, and the very nature of reality itself. Now, let's shift our gaze to one of the most dazzling phenomena in the cosmos, quasars. These celestial powerhouses are the brightest objects in the universe, outshining entire galaxies with their incredible luminosity. But what exactly are quasars, and how does the speed of light play a role in our understanding of these cosmic beacons? Quasars, short for quasi-stellar radio sources, are the intensely bright centers of distant galaxies powered by supermassive black holes. As matter spirals into these black holes, it heats up to extreme temperatures, releasing vast amounts of energy in the form of light and other radiation. This light travels across the universe at the speed of light, taking billions of years to reach us. When we observe a quasar, we're essentially looking back in time, seeing the universe as it was when the light began its journey. The sheer distance that quasar light travels is mind-boggling. Some quasars are so far away that their light has been traveling for more than 10 billion years, meaning we're seeing them as they were when the universe was still in its infancy. This makes quasars not just bright objects, but also invaluable tools for studying the early universe. By analyzing the light from quasars, astronomers can learn about the conditions of the cosmos billions of years ago, including the formation of galaxies and the distribution of matter. The speed of light is crucial here because it allows us to measure these vast distances. The farther away a quasar is, the longer its light has been traveling, and the more it tells us about the universe's history. Quasar light also interacts with the material it passes through, leaving behind clues about the composition and structure of the universe. For example, when quasar light passes through clouds of gas, certain wavelengths are absorbed, creating a unique fingerprint that scientists can analyze to understand the properties of those clouds. Quasars also challenge our understanding of physics. The energy they emit is so immense that it defies easy explanation. In fact, a single quasar can outshine a galaxy containing hundreds of billions of stars. This incredible brightness, combined with the speed of light, allows quasars to serve as cosmic lighthouses, illuminating the distant reaches of the universe and helping astronomers map its large-scale structure. But quasars aren't just relics of the past. Some are still active today, continuing to shape their host galaxies and influence the surrounding cosmos. The light they emit, traveling at the speed of light, connects us to these distant events, offering a glimpse into the dynamic and ever-changing nature of the universe. So, while quasars may seem like distant, ancient objects, they're deeply intertwined with our understanding of the cosmos. Their light, racing across the universe at the speed of light, carries with it the story of the universe's evolution from its earliest moments to the present day. As we continue to study these brilliant objects, they illuminate not just the darkness of space, but also the mysteries of time, distance, and the very fabric of reality. Now, let's journey even further back in time to uncover the oldest light in the universe, the cosmic microwave background radiation. This faint glow, often referred to as the afterglow of the Big Bang, is the most ancient light we can observe, and it has been traveling through space for an astonishing 13.8 billion years. But what exactly is this cosmic microwave background, and why is it so important to our understanding of the universe? The cosmic microwave background, or CMB for short, is the residual heat left over from the Big Bang. Imagine the universe as a newborn glowing with intense heat and energy. As it expanded and cooled over billions of years, that initial burst of light stretched and faded, eventually becoming the faint microwave radiation we detect today. This light is everywhere, filling the entire universe, and it serves as a snapshot of the cosmos when it was just 380,000 years old. At that time, the universe was hot and dense, but as it expanded, the light from that era began its long journey across space and time. The speed of light plays a critical role here. Because light travels at a constant speed, the CMB allows us to peer back to the very early moments of the universe. When we observe this ancient light, we're essentially looking at the universe as it was before galaxies, stars, or even atoms had fully formed. It's like opening a time capsule that reveals the universe's infancy, offering clues about its origins and evolution. One of the most fascinating aspects of the CMB is its uniformity. No matter where we look in the sky, the temperature of this radiation is nearly the same, varying by only tiny fractions of a degree. These minute fluctuations, however, are incredibly significant. They represent the seeds of all the structures we see in the universe today: galaxies, clusters of galaxies, and even the vast cosmic web. Without these tiny variations, the universe would be a featureless expanse, and we wouldn't exist to observe it. The discovery of the cosmic microwave background in 1965 was a monumental moment in science. It provided the strongest evidence yet for the Big Bang theory, confirming that the universe had a beginning and has been expanding ever since. Since then, missions like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have mapped the CMB in exquisite detail, revealing its subtle patterns and deepening our understanding of the universe's composition, age, and fate. But the CMB isn't just a relic of the past. It continues to shape our understanding of the cosmos today. By studying its properties, scientists have determined that the universe is made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. These findings have revolutionized our understanding of the universe's structure and its ultimate destiny. The cosmic microwave background is more than just ancient light. It's a window into the universe's earliest moments and a testament to the power of the speed of light. As this light continues its journey across the cosmos, it carries with it the story of everything, from the fiery birth of the universe to the intricate web of galaxies we see today. And as we decode its secrets, we come closer to understanding not just where we came from, but also where we're headed in this vast, ever-expanding universe. Now let's shift our focus to one of the most fundamental tools in cosmology, the Hubble constant. This key measurement helps us understand how fast the universe is expanding, and it's deeply connected to the speed of light. But what exactly is the Hubble constant, and why does it matter so much in our quest to unravel the mysteries of the cosmos? The Hubble constant is a number that tells us how quickly galaxies are moving away from each other as the universe expands. Think of it like this: imagine the universe as a loaf of raisin bread baking in an oven. As the bread rises, the raisins representing galaxies move farther apart. The Hubble constant is essentially the rate at which that bread is expanding. And just like the speed of light, it's a crucial piece of the puzzle when it comes to understanding the universe's past, present, and future. But here's where the speed of light comes into play. To measure the Hubble constant, astronomers rely on the light emitted by distant galaxies. By observing how fast these galaxies are moving away from us, they can calculate the rate of expansion. However, because light takes time to travel across the vast distances of space, what we're seeing is actually the universe's past. The farther away a galaxy is, the longer its light has been traveling, and the further back in time we're looking. This means the Hubble constant isn't just a snapshot of the universe today, it's a window into its history. The speed of light is essential for these calculations because it allows us to determine how far away these galaxies are. By measuring the redshift of light, how much its wavelength has stretched as the universe expands, scientists can figure out how fast a galaxy is moving away from us. Combine that with the time it took for the light to reach us, and you've got the Hubble constant. It's a delicate dance between distance, speed, and time, all made possible by the constant speed of light. Interestingly, the Hubble constant isn't just a single, fixed number. Over the years, different methods of measuring it have produced slightly different results, leading to what's known as the Hubble tension. Some measurements, like those from the cosmic microwave background, suggest a slower rate of expansion, while others, like observations of nearby galaxies, point to a faster rate. This discrepancy has sparked intense debate among scientists, as it could hint at new physics or even a deeper understanding of dark energy, the mysterious force driving the universe's accelerated expansion. Despite these challenges, the Hubble constant remains one of the most important tools in cosmology. It not only helps us measure the universe's expansion, but also provides clues about its age and ultimate fate. By combining the Hubble constant with other observations, like the cosmic microwave background, scientists have estimated the universe to be around 13.8 billion years old. And as we continue to refine our measurements, we're getting closer to understanding whether the universe will keep expanding forever or eventually slow down. The speed of light, as always, is at the heart of these discoveries. Without it, we wouldn't be able to measure the Hubble constant or unravel the story of the universe's expansion. It's a reminder that even the most distant galaxies and the oldest light are connected by the same fundamental laws that govern our everyday lives. And as we continue to explore the cosmos, the Hubble constant will remain a guiding light, helping us navigate the ever-expanding universe. Now, let's turn our attention to one of the most groundbreaking tools in modern astronomy, the James Webb Space Telescope. This incredible instrument is designed to capture light from the earliest galaxies, giving us a glimpse into the universe's infancy. But how does it do this, and why is the speed of light so crucial to its mission? The James Webb Space Telescope, often referred to as Webb, is like a time machine. It doesn't travel through time, of course, but it allows us to peer back into the past by observing light that has been traveling across the cosmos for billions of years. Because light takes time to reach us, the farther away an object is, the older the light we're seeing. Webb is specifically designed to detect infrared light, which is key to studying the universe's earliest moments. Why? Because as the universe expands, the light from those ancient galaxies gets stretched into longer, redder wavelengths, what we call redshift. Webb's advanced instruments are perfectly tuned to pick up this faint, ancient light. But here's where the speed of light becomes essential. When Webb captures light from a galaxy that's, say, 13 billion light-years away, it's not just showing us a distant object, it's showing us what that galaxy looked like 13 billion years ago. That's because the light we're seeing today left that galaxy when the universe was in its infancy, just a few 100 million years old. Without the constant speed of light, we wouldn't be able to make these incredible connections between distance and time. One of Webb's most exciting discoveries so far has been the detection of some of the earliest galaxies ever observed. These galaxies formed during a period known as the Cosmic Dawn, when the first stars and galaxies began to light up the universe. By studying the light from these ancient objects, scientists can learn about the conditions of the early universe, how galaxies formed, and how they evolved over billions of years. It's like uncovering the universe's baby photos, giving us a clearer picture of how everything we see today came to be. The speed of light also plays a role in Webb's ability to study exoplanets, planets orbiting other stars. When a planet passes in front of its star, some of the star's light passes through the planet's atmosphere. Webb can analyze this light to determine the atmosphere's composition, looking for signs of water, methane, or even potential biosignatures. But because this light has traveled across vast distances at the speed of light, what we're seeing is a snapshot of that planet's atmosphere from the past. It's a reminder that even when studying nearby stars, we're still looking back in time. What makes Webb truly remarkable is its ability to push the boundaries of what we can see and understand. By capturing light from the earliest galaxies, it's helping us piece together the story of how the universe evolved from a hot, dense state to the vast, complex cosmos we see today. And at the heart of all these discoveries is the speed of light, the constant that allows us to measure, observe, and explore the universe's history. As we continue to analyze the data from Webb, we're not just learning about the past, we're also gaining insights into the future. By understanding how galaxies formed and evolved, we can make predictions about how the universe will continue to change. And once again, the speed of light is our guide, connecting the distant past to the present and helping us unravel the mysteries of the cosmos. Now, let's shift our focus to how the speed of light plays a crucial role in one of the most exciting areas of modern astronomy, the search for exoplanets. These distant worlds orbiting stars beyond our solar system are invisible to the naked eye, but thanks to the speed of light and some ingenious techniques, astronomers have discovered thousands of them. So, how exactly does light help us find these faraway planets? One of the most common methods is called the transit technique. Here's how it works. When an exoplanet passes in front of its host star, it blocks a tiny fraction of the star's light. This slight dip in brightness, which travels to us at the speed of light, can be detected by powerful telescopes like Kepler or TESS. By measuring how much the light dims and how often it happens, scientists can determine the planet's size, orbit, and even its distance from the star. It's like watching a cosmic eclipse from light years away, all made possible because light carries this information across the vastness of space. Another key method is the radial velocity technique, which relies on the gravitational tug of war between a star and its orbiting planet. As a planet orbits, its gravity causes the star to wobble slightly. This motion affects the star's light, shifting its wavelengths in a phenomenon known as the Doppler effect. When the star moves toward us, its light is compressed, appearing bluer. When it moves away, the light stretches, appearing redder. These shifts, traveling at the speed of light, allow astronomers to detect the presence of a planet and estimate its mass. It's a bit like listening to the universe's heartbeat, with light acting as the messenger. But here's where the speed of light adds another layer of intrigue. The light we're analyzing from these stars and their planets isn't just a snapshot of their current state, it's a glimpse into the past. For example, if a star is 50 light years away, the light we're seeing today left that star 50 years ago. That means any exoplanet we detect is being observed as it was half a century ago. It's a reminder that even in our search for new worlds, we're always looking back in time. The speed of light also plays a role in more advanced techniques like direct imaging. While challenging, some telescopes have managed to capture actual images of exoplanets by blocking out the overwhelming light of their host stars. The faint light from the planet itself, traveling at light speed, carries details about its atmosphere and surface. By analyzing this light, scientists can search for signs of water, methane, or even potential biosignatures, clues that might hint at the possibility of life. What makes these discoveries so thrilling is that they're not just about finding new planets, they're about understanding our place in the universe. Every exoplanet detected adds to our knowledge of how planetary systems form and evolve. And once again, the speed of light is at the heart of it all, enabling us to explore worlds that were once beyond our reach. As we continue to refine these techniques and build more advanced telescopes, who knows what other secrets the light from distant stars will reveal. Now, let's dive into another fascinating way the speed of light helps us unravel the mysteries of the universe, the Doppler effect. This phenomenon isn't just something you hear when an ambulance zooms past with its siren blaring. It's also a powerful tool astronomers use to study the movement of stars, galaxies, and even entire cosmic structures. So, how does it work with light? When a celestial object like a star or galaxy moves toward us or away from us, its light undergoes a subtle but measurable change. If the object is moving toward us, the light waves get compressed, shifting toward the blue end of the spectrum. This is called blue shift. On the other hand, if the object is moving away, the light waves stretch out, shifting toward the red end of the spectrum, known as redshift. These shifts happen because the speed of light remains constant, but the motion of the object changes the wavelength of the light we receive. This effect is incredibly useful for measuring how fast celestial objects are moving and in what direction. For example, by analyzing the redshift of distant galaxies, astronomers discovered that the universe is expanding. The farther away a galaxy is, the faster it appears to be moving away from us, a key piece of evidence for the Big Bang theory. The Doppler effect also helps scientists study binary star systems where two stars orbit each other. By measuring the shifts in their light, astronomers can determine their speeds, masses, and even the shape of their orbits. But here's where the speed of light adds another layer of wonder. Because light takes time to travel, the Doppler effect doesn't just tell us about an object's current motion, it gives us a glimpse into its past. For instance, if we observe a galaxy that's billions of light years away, the redshift we measure today reflects how that galaxy was moving billions of years ago. It's like having a time machine that lets us peer into the history of the universe. The Doppler effect isn't limited to distant galaxies either. It's also used to study objects closer to home, like exoplanets. As we discussed earlier, the radial velocity technique relies on the Doppler effect to detect the wobble of a star caused by an orbiting planet. By measuring these tiny shifts in the star's light, scientists can infer the planet's presence, mass, and even its distance from the star. It's a remarkable example of how the speed of light and the Doppler effect work together to reveal the secrets of the cosmos. So, whether it's uncovering the expansion of the universe, mapping the orbits of distant stars, or hunting for exoplanets, the Doppler effect is a vital tool in the astronomer's toolkit. And once again, it's the speed of light that makes it all possible, carrying these subtle shifts across the vastness of space and time to help us better understand the universe we live in. Now, let's turn our attention to something equally mesmerizing: the connection between the speed of light and the color of stars. You might have noticed that stars aren't all the same color. Some shine with a cool blue hue, while others glow a warm red. But did you know that these colors aren't just for show? They're actually a direct result of how the speed of light interacts with the energy stars emit, and they hold the key to understanding a star's temperature and age. Here's how it works. Stars produce light through nuclear fusion, a process that generates immense amounts of energy. This energy is released as light, which travels through space at, you guessed it, the speed of light. But not all light is the same. The color of a star depends on its surface temperature, which determines the wavelength of the light it emits. Hotter stars, with surface temperatures reaching tens of thousands of degrees, emit shorter wavelengths of light which appear blue or white to our eyes. Cooler stars, on the other hand, emit longer wavelengths, giving them a reddish glow. This relationship between temperature and color is described by something called Wien's law, which states that the peak wavelength of light emitted by an object is inversely proportional to its temperature. In simpler terms, the hotter the star, the bluer it appears, and the cooler the star, the redder it looks. This principle allows astronomers to determine a star's temperature just by observing its color. For example, our Sun, with a surface temperature of around 5,500 degrees Celsius, emits light that peaks in the yellow part of the spectrum, giving it its characteristic golden glow. But the story doesn't end there. The color of a star also provides clues about its age and stage of life. Younger, more massive stars tend to burn hotter and appear bluer, while older stars, which have exhausted much of their fuel, cool down and take on a reddish hue. By studying the colors of stars, astronomers can piece together the life cycles of these celestial giants, from their fiery births to their eventual fates as dim, cooling remnants. And here's where the speed of light plays a crucial role. Because light takes time to travel, the colors we see from distant stars are actually snapshots of their past. When we observe a star that's thousands or even millions of light years away, we're seeing it as it was when that light began its journey to Earth. This means that by analyzing the colors of stars, we're not just learning about their current states, we're also peering back in time, uncovering the history of stellar evolution across the cosmos. So, the next time you gaze up at the night sky and notice the twinkling colors of the stars, remember that you're witnessing a cosmic dance of light, temperature, and time. The speed of light doesn't just carry these colors to us, it helps us decode the secrets of the universe, one star at a time. Now, let's take a closer look at how the speed of light helps us unravel the fascinating story of a star's life. Stars, much like living beings, go through distinct stages of life, and the light they emit serves as a cosmic diary, chronicling their journey from birth to death. By studying this light, astronomers can piece together the intricate details of stellar evolution, revealing how stars are born, how they live, and how they eventually meet their end. When a star is born, it begins as a dense cloud of gas and dust collapsing under its own gravity. As this material contracts, it heats up, eventually reaching temperatures high enough to ignite nuclear fusion. This is the moment a star is truly born, and it starts emitting light that travels across the universe at the speed of light. In their youth, stars are often hot and bright, shining with a blue or white hue. These young stars, known as main sequence stars, spend the majority of their lives fusing hydrogen into helium, a process that releases vast amounts of energy and keeps them glowing steadily. As stars age, they undergo significant changes. For instance, when a star like our Sun exhausts its hydrogen fuel, it begins to fuse helium into heavier elements. This causes the star to expand into a red giant, a phase where it cools and takes on a reddish glow. The light emitted during this stage tells us not only about the star's current state, but also about the processes happening deep within its core. By analyzing this light, astronomers can determine how much fuel the star has left and predict its future. Eventually, stars reach the end of their lives and their fates depend on their mass. Smaller stars, like our Sun, shed their outer layers and leave behind a dense core called a white dwarf. This remnant slowly cools and fades over billions of years, emitting a faint white light. On the other hand, massive stars end their lives in spectacular supernova explosions, outshining entire galaxies for a brief moment. The light from these explosions travels across the cosmos, carrying with it information about the elements forged in the star's core, which are scattered into space to form new stars and planets. What makes this even more remarkable is that the light we observe from stars is often a snapshot of their past. Because light takes time to travel, we're seeing stars as they were when that light began its journey, sometimes thousands or even millions of years ago. This means that by studying the light from stars at different stages of their life cycles, we're not just learning about individual stars, we're also piecing together the history of star formation and evolution across the universe. So the next time you look up at the night sky, remember that the stars you see are more than just points of light. They're cosmic storytellers, their light carrying tales of birth, life, and death across the vast expanse of space and time. And thanks to the speed of light, we're able to read these stories one photon at a time. Now, let's turn our attention to one of the most dramatic events in the cosmos, supernova. These colossal explosions mark the explosive deaths of massive stars, and the light they emit travels across the universe at the speed of light, giving us a front-row seat to their final moments. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses, triggering a cataclysmic explosion that outshines entire galaxies for a brief period. This light, racing through space at 299,792,458 meters per second, carries with it a wealth of information about the star's final act. What makes supernovae so fascinating is not just their sheer power, but also the role they play in the universe's grand cycle of life and death. During the explosion, elements like iron, gold, and uranium are forged in the star's core and scattered into space. These elements, carried by the light and shockwaves of the supernova, eventually become the building blocks for new stars, planets, and even life itself. By studying the light from supernova, astronomers can determine not only the composition of the star, but also the conditions under which these heavy elements were created. One of the most remarkable aspects of supernova is that their light allows us to witness events that occurred billions of years ago. Because light takes time to travel, we're seeing these explosions as they happened in the distant past. For example, the light from a supernova that occurred in a galaxy 10 million light-years away began its journey 10 million years ago. By the time it reaches us, the star itself is long gone, but its light continues to tell its story. This time delay gives us a unique window into the history of the universe, allowing us to observe how stars lived and died in eras long before our own. Supernovae also serve as cosmic mile markers, helping astronomers measure vast distances across the universe. A specific type of supernova, known as a Type Ia supernova, has a predictable brightness, making it a valuable tool for calculating how far away galaxies are. By comparing the observed brightness of these supernovae to their known intrinsic brightness, scientists can determine the distance to their host galaxies with remarkable precision. This method has been instrumental in discovering the accelerated expansion of the universe, a finding that earned the Nobel Prize in Physics in 2011. The light from supernova doesn't just illuminate the past, it also helps us understand the future. By studying these explosions, scientists can learn more about the processes that drive stellar evolution and the formation of elements essential for life. Each supernova is a cosmic laboratory offering insights into the forces that shape the universe. So, the next time you hear about a supernova, remember that its light is more than just a fleeting flash in the sky. It's a messenger from the depths of space, carrying stories of creation, destruction, and the endless cycle of cosmic renewal. Now, let's shift our focus to one of the most mysterious components of the universe: dark matter. This invisible substance makes up about 85% of all matter in the cosmos, yet it doesn't emit, absorb, or reflect light, making it impossible to observe directly. So, how do we study something we can't see? The answer lies in the speed of light and its interactions with the fabric of space-time. Dark matter's presence is inferred through its gravitational effects on visible matter, such as stars and galaxies. When light from distant objects travels through the universe, it can be bent or distorted by the gravitational pull of dark matter, a phenomenon known as gravitational lensing. By measuring how much the light is bent and how long it takes to reach us, scientists can map the distribution of dark matter in the universe. This technique relies on the constant speed of light, which acts as a cosmic ruler, allowing us to calculate the mass and location of these invisible structures. One of the most striking examples of this is the Bullet Cluster, where two galaxy clusters collided. Observations showed that the visible matter, like gas and dust, slowed down due to friction, while the dark matter passed through unaffected. By analyzing the way light from background galaxies was distorted, astronomers could pinpoint the dark matter's location, proving its existence and revealing its behavior. Without the speed of light as a reference, such discoveries would be impossible. The speed of light also plays a crucial role in simulations and models of the universe. Scientists use it to predict how dark matter should behave over time, helping us understand its role in the formation of galaxies and the large-scale structure of the cosmos. These models rely on the fact that light travels at a constant speed, providing a consistent framework for studying the invisible scaffolding that holds the universe together. While dark matter remains one of the greatest mysteries in modern physics, the speed of light continues to be an essential tool in unraveling its secrets. By studying how light interacts with the unseen, we're slowly piecing together the puzzle of this elusive substance, bringing us closer to understanding the true nature of the universe. So, the next time you think about light, remember that it's not just illuminating the stars, it's also shining a light on the invisible forces that shape our cosmos. Now, let's turn our attention to another cosmic mystery: dark energy. This enigmatic force is responsible for the accelerated expansion of the universe, a discovery that shook the foundations of modern cosmology. But how do we study something as elusive as dark energy? Once again, the speed of light plays a starring role. Dark energy was first discovered in the late 1990s when astronomers observed distant supernovae, the explosive deaths of massive stars. These supernovae, known as Type 1a, act as standard candles because they emit a consistent amount of light. By measuring how bright these supernovae appear from Earth and comparing it to their known brightness, scientists can calculate how far away they are. But here's where things get fascinating. These supernovae were dimmer than expected, meaning they were farther away than predicted. This suggested that the universe wasn't just expanding, it was accelerating. The speed of light is crucial in these calculations. Light from these supernovae travels billions of years to reach us, and by measuring the time it takes and the redshift of the light, how much its wavelength has stretched due to the expansion of the universe, scientists can determine how fast the universe is expanding. This data revealed that something was pushing galaxies apart faster and faster over time. That something is dark energy, a force that makes up about 68% of the universe's total energy. But what exactly is dark energy? That's still one of the biggest questions in physics. Some theories suggest it's a property of space itself, often referred to as the cosmological constant, a concept Einstein once proposed and later dismissed. Others think it might be a dynamic field that changes over time. Whatever it is, the speed of light remains our primary tool for studying it. By observing the light from more distant supernovae and other cosmic phenomena, like the cosmic microwave background, scientists are piecing together the puzzle of dark energy and its role in shaping the fate of the universe. So, while dark energy remains invisible and mysterious, the speed of light continues to illuminate its effects, helping us understand the forces driving the cosmos apart. It's a reminder that even the most elusive aspects of the universe leave traces in the light that travels across the vast expanse of space and time. Now, let's venture into one of the most mind-bending ideas in modern physics, the multiverse theory. Imagine a reality where our universe is just one of countless others, each with its own unique set of physical laws. Could the speed of light be different in these other universes? The answer might just reshape everything we think we know about reality. The multiverse theory suggests that our universe is part of a vast, possibly infinite collection of universes. Some of these universes might have entirely different constants of nature, including the speed of light. In our universe, light travels at a constant speed of about 299,792,458 meters per second in a vacuum. But in another universe, that speed could be faster, slower, or even non-existent if light behaves differently there. This idea isn't just science fiction, it's a serious topic of discussion among physicists. If the speed of light were different in another universe, it would fundamentally alter the way time, space, and matter interact. For example, a universe with a faster speed of light might have shorter distances between stars and galaxies, making interstellar travel more feasible. On the other hand, a slower speed of light could mean that time itself flows differently, potentially leading to entirely new forms of physics. But how do we even begin to explore such a concept? While we can't directly observe other universes, scientists use mathematical models and theoretical frameworks to explore these possibilities. Some theories, like string theory, suggest that the multiverse could exist in higher dimensions, with each universe occupying its own brain or membrane. In these models, the speed of light might vary depending on the properties of each brain. The implications are staggering. If the speed of light isn't a universal constant across all realities, it could mean that the laws of physics we take for granted are just one possibility among many. This raises profound questions about the nature of existence itself. Are we living in the only universe where life is possible, or are there countless others where life has evolved under entirely different rules? While the multiverse theory remains speculative, it's a fascinating reminder of how much we still have to learn about the cosmos. The speed of light, a cornerstone of our understanding of the universe, might just be one piece of a much larger puzzle, one that stretches across dimensions we can't yet imagine. And as we continue to explore these ideas, the mysteries of the multiverse remind us that the universe or universes are far stranger and more wonderful than we've ever dreamed. Now, let's take a leap into the realm of wormholes, a concept that sounds like it's straight out of science fiction, but is deeply rooted in the equations of general relativity. Wormholes, often called Einstein-Rosen bridges, are theoretical tunnels through spacetime that could connect two distant points in the universe. Imagine folding a piece of paper so that 2 points touch. That's essentially what a wormhole does, creating a shortcut that bypasses the vast distances of space. But how does this relate to the speed of light? In our universe, the speed of light is the ultimate speed limit. Nothing can travel faster than light, which means crossing the immense distances between stars and galaxies would take thousands or even millions of years. Wormholes, however, offer a tantalizing possibility. They could allow us to traverse these distances almost instantaneously, effectively sidestepping the speed of light barrier. Here's where it gets even more fascinating. According to Einstein's theory of general relativity, wormholes could exist as solutions to the equations that describe spacetime. These tunnels would be held open by exotic matter, a hypothetical substance with negative energy density that counteracts the natural tendency of the wormhole to collapse. Without this exotic matter, the wormhole would snap shut faster than light could pass through it. But don't pack your bags for an interstellar journey just yet. Wormholes remain purely theoretical, and there's no experimental evidence to prove their existence. Even if they do exist, they'd likely be incredibly unstable, vanishing almost as quickly as they form. Plus, the exotic matter required to keep them open is something we've never observed in nature. Still, the idea of wormholes opens up thrilling possibilities. If we could harness them, they'd revolutionize space travel, allowing us to explore distant galaxies without being bound by the speed of light. They also raise intriguing questions about the nature of spacetime itself. Could wormholes connect not just distant places but different times? Could they serve as portals to other universes, as some theories suggest? While wormholes remain a mystery, they remind us that the universe is full of wonders we've only begun to imagine. The speed of light, once thought to be an insurmountable barrier, might one day be bypassed through the strange and beautiful geometry of spacetime. And as we continue to explore these ideas, the line between science and science fiction grows ever thinner, inviting us to dream of what might lie beyond the stars. Now, let's shift our focus to one of the most mind-bending ideas in physics: the connection between the speed of light and time travel. This concept isn't just the stuff of science fiction, it's grounded in the principles of Einstein's theory of relativity. According to relativity, as an object approaches the speed of light, time begins to slow down for that object relative to an outside observer. This phenomenon, known as time dilation, opens the door to some fascinating possibilities. Imagine you're on a spaceship traveling at close to the speed of light. For you, time would pass normally, but for someone back on Earth, years or even decades could go by in what feels like just a few moments to you. This means that, in theory, you could travel into the future simply by moving fast enough. It's like hitting the fast-forward button on time itself. But here's the catch: while you could travel forward in time, going backward, true time travel to the past remains a much more complicated challenge. One of the most famous thought experiments exploring this idea is the twin paradox. Picture two twins. One stays on Earth while the other embarks on a high-speed journey through space. When the traveling twin returns, they'll find that they've aged much less than their sibling on Earth. This isn't just a hypothetical scenario. It's been confirmed by experiments with atomic clocks on fast-moving airplanes and satellites. Time dilation is real, and it's a direct consequence of the speed of light being a universal constant. But what about traveling back in time? Some theories suggest that if you could exceed the speed of light, you might be able to bend time in such a way that you could revisit the past. However, this idea runs into a major problem. According to our current understanding of physics, nothing can travel faster than light. The speed of light isn't just a speed limit, it's a fundamental property of the universe. Breaking this rule would require rewriting the laws of physics as we know them. Another intriguing possibility involves wormholes, which we touched on earlier. If wormholes exist, they might not only connect distant points in space but also different points in time. This could create a pathway for time travel, allowing you to move backward or forward through time. But as with wormholes themselves, this remains purely theoretical. The challenges of stabilizing a wormhole and the need for exotic matter make it a distant dream, at least for now. The idea of time travel also raises some profound questions. If we could travel back in time, would we be able to change the past, or would the universe enforce some kind of cosmic rule to prevent paradoxes, like the famous grandfather paradox? These questions push the boundaries of our understanding and remind us that the universe is far stranger and more complex than we can imagine. While time travel remains a tantalizing possibility, it's one that comes with immense challenges. The speed of light, as both a barrier and a gateway, continues to shape our understanding of time and space. As we explore these ideas, we're reminded that the universe is full of mysteries waiting to be unraveled, and that the journey to uncover them is just as exciting as the destination. Now, let's turn our attention to one of the most intriguing questions in science. Are we alone in the universe? This brings us to the Fermi paradox, which asks why, given the vastness of the cosmos and the high probability of extraterrestrial life, we haven't found any evidence of it yet. One of the key factors in this mystery is the speed of light, which plays a crucial role in limiting interstellar communication and exploration. The speed of light, as we've discussed, is the ultimate speed limit in the universe. This means that any signal or message sent across the stars would take years, centuries, or even millennia to reach its destination, depending on how far away the target is. For example, if an alien civilization were located 100 light-years away, any message we send them today wouldn't arrive for 100 years, and we'd have to wait another 100 years for a reply. This creates a significant barrier to real-time communication and makes the search for extraterrestrial intelligence a game of patience and persistence. But the challenges don't stop there. The vast distances between stars also mean that even if intelligent life exists elsewhere, the likelihood of two civilizations existing close enough to communicate within a reasonable time frame is incredibly slim. Imagine trying to have a conversation with someone on the other side of the planet, but instead of waiting seconds for a reply, you're waiting centuries. It's no wonder that finding evidence of alien life has proven so difficult. Another layer to this puzzle is the sheer age of the universe. Civilizations may have risen and fallen long before we even existed, their signals lost in the vastness of space. Or perhaps they're so far ahead of us technologically that their methods of communication are beyond our current understanding. The speed of light ensures that we're essentially looking into the past when we observe distant stars and galaxies, adding another layer of complexity to the search. So, what does this mean for the Fermi paradox? It suggests that the speed of light isn't just a physical barrier, it's a cosmic filter that makes interstellar communication and contact incredibly challenging. It's possible that advanced civilizations are out there, but the limitations imposed by the speed of light mean that we might never cross paths or exchange messages. This doesn't mean we should stop looking, though. In fact, it makes the search even more fascinating, as every discovery brings us closer to understanding our place in the universe. As we ponder the implications of the speed of light on the Fermi paradox, we're reminded of just how vast and mysterious the cosmos truly is. The search for extraterrestrial life is not just about finding aliens, it's about exploring the boundaries of what's possible and uncovering the secrets of the universe itself. And who knows, one day we might just find that we're not alone after all. Now, let's shift our focus to another fascinating concept that ties the speed of light to our search for extraterrestrial life, the Drake equation. This equation, proposed by astronomer Frank Drake in the 1960s, is a way to estimate the number of intelligent civilizations in our galaxy that might be capable of communicating with us. While it's not a definitive answer, it's a framework that helps us think about the possibilities, and the speed of light plays a key role in shaping those possibilities. The Drake equation considers several factors such as the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. But one of the most critical factors is the average lifespan of a communicating civilization. Why? Because even if intelligent life exists, the speed of light limits how far their signals can travel and how long those signals might last. If a civilization only broadcasts for a few hundred years before collapsing or evolving beyond communication, their signals might never reach us, or they might arrive long after the civilization is gone. Think of it this way: the speed of light acts like a cosmic timer. Signals from distant civilizations can only travel so fast, and by the time they reach us, the civilization that sent them might no longer exist. This means that even if the Drake equation suggests there are many intelligent civilizations out there, the speed of light could make it nearly impossible for us to detect them. It's like trying to catch a message in a bottle that's been floating in the ocean for centuries. You might find it, but the person who sent it is long gone. This also raises an interesting question: how long do civilizations typically last? If they're short-lived, the chances of overlapping with another civilization's communication window are slim. But if they're long-lived, the speed of light still creates a delay that could span generations. For example, if a civilization 1,000 light-years away sent us a message today, we wouldn't receive it for 1,000 years, and by then, who knows what state they or we would be in. The Drake equation doesn't give us a clear answer, but it does highlight the challenges posed by the speed of light. It reminds us that even if the galaxy is teeming with intelligent life, the vast distances and the limitations of light speed might keep us forever isolated. Yet, this doesn't mean the search is futile. In fact, it makes every discovery, or even the absence of one, a piece of the puzzle in understanding our place in the cosmos. As we continue to explore the implications of the Drake equation, we're reminded that the speed of light isn't just a number. It's a fundamental constraint that shapes our understanding of the universe and our quest to find others like us. And while the challenges are immense, the possibilities are endless, making the search for extraterrestrial intelligence one of the most exciting endeavors in science. Now, let's turn our attention to a thought-provoking idea that ties the speed of light to one of the most intriguing questions in science: the Great Filter Hypothesis. This concept suggests that there's some kind of barrier, a filter, that prevents civilizations from reaching an advanced stage or surviving long enough to make contact with others. The speed of light plays a crucial role in this theory, shaping how we think about the challenges of interstellar communication and the survival of intelligent life. The Great Filter could exist at any stage of a civilization's development. It might be something that prevents life from forming in the first place, like the rarity of habitable planets. Or it could be a hurdle that arises later, such as self-destruction through war, environmental collapse, or other existential threats. If the filter lies in our past, it means we've already overcome it, and the universe might be teeming with civilizations like ours. But if it lies ahead, it could mean that advanced civilizations rarely survive long enough to explore the stars, and that's where the speed of light comes into play. Imagine a civilization that has overcome all the challenges of survival and is ready to explore the cosmos. Even if they develop the technology to send signals or spacecraft across vast distances, the speed of light imposes a hard limit on how quickly they can communicate or travel. A message sent to a star system 1,000 light-years away would take 1,000 years to arrive, and a response would take another 1,000 years to return. By the time the conversation even begins, the civilization that sent the original message might no longer exist. This delay could make meaningful communication, or even the discovery of other civilizations, nearly impossible. The speed of light also affects how we interpret the silence of the universe. If advanced civilizations are out there, why haven't we heard from them? One possibility is that they've already passed through the great filter and disappeared, leaving behind only faint traces of their existence. Another is that they're still out there, but the vast distances and the limitations of light speed make it impossible for us to detect them. In either case, the speed of light acts as a kind of cosmic curtain, hiding the answers to some of our biggest questions. This leads us to an even deeper question. Could the great filter be tied to the speed of light itself? If faster-than-light travel or communication is impossible, as our current understanding of physics suggests, then the universe might be designed in a way that keeps civilizations isolated. The vast distances between stars, combined with the finite speed of light, could create a natural barrier that prevents civilizations from ever meeting or even knowing about each other. This isolation might be the ultimate great filter, ensuring that intelligent life remains rare and scattered across the cosmos. As we ponder the great filter and the role of the speed of light, we're reminded of just how fragile and fleeting our existence might be. The challenges of interstellar communication and survival are immense, but they also inspire us to keep searching, learning, and pushing the boundaries of what's possible. After all, the universe is full of mysteries, and every discovery brings us one step closer to understanding our place within it. Now, let's shift our focus to a fascinating framework that helps us imagine the potential of advanced civilizations, the Kardashev scale. This scale, proposed by the Soviet astronomer Nikolai Kardashev in the 1960s, classifies civilizations based on their ability to harness and use energy. It's a way to measure how far a civilization has progressed, from harnessing the energy of their home planet to controlling the energy of an entire galaxy. But here's the catch: the speed of light plays a critical role in limiting how far these civilizations can expand and communicate. At the lowest level, a Type 1 civilization has mastered the energy of its own planet. Think of a society that can control weather, tap into geothermal energy, and harness the full power of its sun. A Type 2 civilization, on the other hand, has gone even further, capturing the energy of its entire star, perhaps by building something like a Dyson sphere, a massive structure that surrounds a star to collect its energy. And then there's the ultimate goal, a Type 3 civilization which can harness the energy of an entire galaxy. But here's where the speed of light becomes a major hurdle. Even for a Type 3 civilization, the vast distances between stars and galaxies, combined with the finite speed of light, make it incredibly difficult to coordinate and expand across such enormous scales. Imagine a civilization trying to send a message or a spacecraft to another star system. Even if they've mastered the energy of their galaxy, the speed of light means that communication and travel would still take thousands or even millions of years. A message sent from one end of the Milky Way to the other would take around 100,000 years to arrive. By the time the message is received, the civilization that sent it might have evolved into something entirely different or even disappeared altogether. This limitation raises a profound question. Could the speed of light act as a kind of cosmic barrier, preventing even the most advanced civilizations from truly unifying or expanding beyond their local region? The Kardashev scale also highlights another intriguing possibility. If a civilization reaches Type 3 status, it might develop technologies that allow it to work around the limitations of light speed. For example, they could use wormholes, hypothetical shortcuts through space-time, to travel vast distances instantly, or they might rely on quantum entanglement to communicate faster than light, though this remains purely theoretical. But even with these possibilities, the speed of light remains a fundamental constraint, shaping how civilizations grow, communicate, and explore the universe. As we consider the Kardashev scale and the role of the speed of light, we're reminded of just how vast and complex the universe truly is. The challenges of energy, distance, and time are immense, but they also inspire us to dream of what might be possible. Whether we're a Type 0 civilization just beginning to explore our own planet or imagining the distant future of a Type 3 society, the speed of light remains a constant reminder of the boundaries and the possibilities that define our place in the cosmos. Now, let's take a closer look at one of the most ambitious dreams of humanity, interstellar travel. The idea of traveling to distant stars has captivated our imaginations for centuries, but the reality of such journeys is shaped by one undeniable factor: the speed of light. Even with the most advanced technology we can envision, the vast distances between stars present a monumental challenge. For example, the closest star system to Earth, Alpha Centauri, is about 4.37 light-years away. That means even if we could travel at the speed of light, it would still take over 4 years to reach it. And here's the catch: according to our current understanding of physics, nothing can travel faster than light. This limitation creates a significant barrier for interstellar travel. To put it into perspective, consider our fastest spacecraft to date, like the Parker Solar Probe, which travels at speeds of up to 430,000 miles per hour. At that rate, it would take tens of thousands of years to reach even the nearest stars. The sheer scale of these distances makes it clear that traditional propulsion methods like chemical rockets are simply not up to the task. Even if we could build a spacecraft capable of traveling at a significant fraction of light speed, the energy requirements would be staggering. Accelerating a spacecraft to such speeds would require an amount of energy far beyond anything humanity has ever produced. But the challenges don't end there. Traveling at such high speeds introduces other complications, like the effects of time dilation predicted by Einstein's theory of relativity. For a spacecraft traveling close to the speed of light, time would pass more slowly for the crew compared to those on Earth. This means that while the journey might feel like a few years for the travelers, decades or even centuries could pass on Earth. Imagine leaving on a mission to a distant star, only to return and find that everyone you knew has aged or passed away. It's a sobering reminder of the profound impact the speed of light has on our ability to explore the cosmos. Despite these challenges, scientists and engineers are exploring innovative solutions to make interstellar travel a reality. Concepts like light sails, which use the pressure of light from lasers to propel spacecraft, could potentially reach speeds of up to 20% the speed of light. Other ideas, such as antimatter propulsion or harnessing the power of black holes, remain in the realm of theoretical physics but offer tantalizing possibilities. While these technologies are still far from being realized, they remind us that the speed of light, while a formidable barrier, also inspires us to push the boundaries of what's possible. As we ponder the future of interstellar travel, we're reminded of both the incredible potential and the immense challenges that lie ahead. The speed of light may limit how quickly we can reach the stars, but it also fuels our curiosity and determination to explore the unknown. Whether through breakthroughs in physics or bold new technologies, the dream of traveling to distant worlds continues to drive humanity forward, reminding us that the universe is full of wonders waiting to be discovered. Now let's shift our focus to a fascinating concept that could one day make interstellar travel possible, despite the limitations imposed by the speed of light: generation ships. These are massive spacecraft designed to carry entire communities of humans across the vast distances between stars. The idea is that multiple generations would live, work, and die aboard the ship before it ever reaches its destination. It's a concept that blends science fiction with real-world challenges, offering a potential solution to the problem of traveling to stars that are light years away. The concept of generation ships hinges on the reality that, with our current understanding of physics, reaching even the nearest stars would take centuries. For example, a journey to Alpha Centauri, the closest star system to Earth, would take over 4 years at the speed of light. But since we can't achieve that speed, the trip would likely take thousands of years using conventional propulsion methods. Generation ships address this by creating a self-sustaining environment where humans can thrive for the duration of the journey. These ships would need to be equipped with everything necessary for life: food production, water recycling, energy generation, and even social structures to maintain a stable society over generations. One of the biggest challenges of generation ships is ensuring the survival and well-being of the crew over such an extended period. The ship would need to be a closed ecosystem, capable of recycling resources indefinitely. Any failure in this system could spell disaster for the entire mission. Additionally, the psychological and social dynamics of a multi-generational crew would be incredibly complex. Imagine being born on a ship, knowing that your great-great-grandchildren might be the ones to finally reach the destination. Maintaining morale, purpose, and cohesion over such a long time span would require careful planning and innovative solutions. Despite these challenges, generation ships represent a bold vision for humanity's future in the cosmos. They remind us that the speed of light, while a barrier, doesn't have to be a dead end. By thinking creatively and planning for the long term, we might one day overcome the vast distances that separate us from the stars. And while the idea of spending entire lifetimes aboard a spacecraft might seem daunting, it also highlights the resilience and adaptability of humanity. After all, exploration has always been about pushing boundaries and venturing into the unknown, no matter how long the journey takes. As we consider the possibilities of generation ships, we're reminded that the speed of light isn't just a limit, it's also a challenge that inspires us to dream bigger and think further ahead. Whether through generation ships or other innovative solutions, the dream of reaching the stars continues to drive us forward, proving that even the most daunting obstacles can be overcome with ingenuity and determination. Now, let's explore another intriguing concept that could revolutionize long-duration space travel: cryosleep. Imagine being able to put astronauts into a state of suspended animation, slowing down their biological processes so that they can endure the vast stretches of time required to travel between stars. This idea, often seen in science fiction, is being seriously considered as a potential solution to the challenges of interstellar journeys at sublight speeds. Cryosleep, or cryogenic sleep, involves cooling the human body to extremely low temperatures, effectively putting it into a state of hibernation. In this state, the body's metabolic rate would slow down dramatically, reducing the need for food, water, and oxygen. This could allow astronauts to survive for decades or even centuries without aging significantly, making it possible to travel to distant star systems without the need for generation ships or other long-term living arrangements. One of the biggest advantages of cryosleep is its potential to minimize the psychological and social challenges of long-duration space travel. Instead of spending entire lifetimes aboard a spacecraft, astronauts could simply sleep through the journey, waking up only when they reach their destination. This would eliminate the need for complex social structures and multi-generational planning, making interstellar missions more feasible with smaller crews and fewer resources. However, cryosleep is not without its challenges. The technology required to safely induce and reverse suspended animation is still in its infancy. Scientists would need to find a way to prevent cellular damage caused by freezing, as well as develop methods to safely revive individuals after long periods of dormancy. Additionally, the long-term effects of cryosleep on the human body and mind are still largely unknown, raising questions about the feasibility and safety of this approach. Despite these hurdles, cryosleep represents a promising avenue for overcoming the limitations imposed by the speed of light. By allowing humans to pause their biological clocks, we could potentially bridge the vast distances between stars without the need for faster-than-light travel. It's a concept that combines cutting-edge science with the timeless human desire to explore the unknown, offering a glimpse into a future where the stars are within our reach. As we continue to push the boundaries of what's possible, cryosleep reminds us that the challenges of space travel are not insurmountable. With innovation and determination, we may one day find a way to traverse the cosmos, not by breaking the speed of light, but by redefining what it means to travel through time and space. Now, let's shift our focus to a fascinating concept that could one day propel spacecraft to incredible speeds without the need for traditional fuel: light sails. Imagine harnessing the power of light itself to push a spacecraft through the vastness of space. This isn't science fiction, it's a real technology being developed to overcome the limitations of conventional propulsion systems. Light sails work by using the pressure of light to generate thrust. When photons, the particles of light, strike a reflective surface, they transfer a tiny amount of momentum to it. While this force is incredibly small, in the vacuum of space where there's no friction to slow things down, even this minuscule push can add up over time. By deploying a large, ultra-thin sail made of highly reflective material, a spacecraft could catch the momentum of light from the sun or powerful lasers, gradually accelerating to significant fractions of the speed of light. One of the most exciting aspects of light sails is their potential to reach speeds that would make interstellar travel feasible. Unlike chemical rockets, which require massive amounts of fuel and are limited by the energy they can carry, light sails rely on an external source of energy: light itself. This means they could theoretically keep accelerating as long as they're exposed to a strong enough light source, allowing them to achieve velocities that would otherwise be impossible with current technology. Projects like the Breakthrough Starshot initiative are already exploring the possibilities of light sails. The idea is to send tiny, lightweight probes equipped with light sails to nearby star systems propelled by powerful ground-based lasers. These probes could reach speeds of up to 20% the speed of light, making it possible to reach Alpha Centauri, our nearest stellar neighbor, in just a couple of decades. Of course, light sails aren't without their challenges. Building a sail large enough to capture sufficient light while remaining lightweight and durable is no easy task. Additionally, precise control and navigation will be required to ensure the spacecraft stays on course over such vast distances. But despite these hurdles, light sails represent a groundbreaking approach to space travel, one that could open up the stars to exploration in ways we've only dreamed of. As we continue to push the boundaries of what's possible, light sails remind us that sometimes the most powerful solutions come from the simplest ideas. By harnessing the gentle pressure of light, we might one day unlock the secrets of the cosmos, traveling farther and faster than ever before. And with that, we move closer to a future where the stars are no longer out of reach. Now, let's venture into a realm of physics that sounds like it's straight out of science fiction, but is grounded in real scientific exploration: antimatter propulsion. Imagine a fuel so powerful that just a tiny amount could propel a spacecraft to speeds approaching the speed of light. That's the promise of antimatter, the mysterious counterpart to the matter that makes up our everyday world. Antimatter is essentially the mirror image of ordinary matter. For every particle of matter, like an electron, there's an antimatter counterpart, in this case a positron. When matter and antimatter meet, they annihilate each other, releasing an enormous amount of energy. In fact, this process is the most efficient energy conversion known to science, far surpassing even nuclear reactions. A single gram of antimatter could produce as much energy as tens of thousands of tons of chemical rocket fuel. This incredible energy density makes antimatter an ideal candidate for powering spacecraft to near light speeds. The idea is to use the energy released from matter-antimatter annihilation to generate thrust, potentially allowing spacecraft to reach velocities that would make interstellar travel feasible. Unlike traditional propulsion methods, which are limited by the amount of fuel they can carry, antimatter propulsion could offer a lightweight, high-energy solution for long-distance space travel. However, there are significant challenges to overcome. Producing and storing antimatter is incredibly difficult and expensive. Currently, antimatter is created in particle accelerators, but only in minuscule amounts. Storing it is equally tricky, as antimatter must be kept isolated from matter to prevent premature annihilation. Special magnetic fields are used to contain it, but even the slightest error could result in catastrophic energy release. Despite these hurdles, researchers are actively exploring ways to harness antimatter for propulsion. Concepts like antimatter-catalyzed nuclear propulsion aim to use small amounts of antimatter to trigger nuclear reactions, providing a more practical approach than pure antimatter engines. These systems could still achieve remarkable speeds while reducing the risks and costs associated with handling large quantities of antimatter. The potential of antimatter propulsion is staggering. If we can overcome the technical challenges, it could revolutionize space travel, enabling missions to distant stars within a human lifetime. It's a reminder that the universe holds incredible possibilities, and with ingenuity and perseverance, we might one day unlock the secrets of antimatter to explore the cosmos like never before. And with that, we turn to another groundbreaking concept that pushes the boundaries of what we thought was possible: the Breakthrough Starshot Initiative. Now, let's shift our focus to a project that sounds like it's straight out of a sci-fi movie, but is very much rooted in real-world science: the Breakthrough Starshot Initiative. This ambitious project aims to send tiny, lightweight probes to our nearest star system, Alpha Centauri, at an astonishing 20% of the speed of light. To put that into perspective, traveling at that speed would allow these probes to reach Alpha Centauri in just about 20 years, a journey that would take tens of thousands of years with current propulsion technology. The Breakthrough Starshot Initiative is built around the concept of light sails, which we touched on earlier. These sails would be propelled not by wind like traditional sails, but by powerful lasers fired from Earth. The idea is to attach ultra-thin, reflective sails to miniature probes, each no larger than a postage stamp. When the lasers hit the sails, they would push the probes forward, accelerating them to a fraction of the speed of light. It's a bit like using a beam of light to give these tiny spacecraft a cosmic push. One of the biggest challenges of this project is the sheer scale of engineering required. The lasers used to propel the probes would need to be incredibly powerful, capable of generating a beam with the energy of millions of lasers combined. Additionally, the light sails would have to be made of materials that are both incredibly lightweight and highly reflective to maximize the efficiency of the laser propulsion. Even the tiniest imperfection in the sail's design could throw the probe off course given the immense speeds involved. But why Alpha Centauri? This star system, located just over 4 light-years away, is the closest neighboring system to our own. It's home to Proxima Centauri, a star that hosts at least one confirmed exoplanet in its habitable zone, meaning it could potentially support liquid water and perhaps life. Sending probes to Alpha Centauri would give us our first close-up look at another star system and could provide invaluable data about its planets and environment. The Breakthrough Starshot initiative isn't just about reaching another star, it's about redefining what's possible in space exploration. By leveraging the speed of light and cutting-edge technology, this project could open the door to interstellar travel, allowing humanity to explore the cosmos in ways we've only dreamed of. While the challenges are immense, the potential rewards are equally staggering. And with that, we move to another fascinating concept that ties the speed of light to one of the most intriguing thought experiments in physics, the twin paradox. Now, let's dive into one of the most mind-bending consequences of traveling near the speed of light, the twin paradox. Imagine two identical twins, let's call them Alex and Jamie. Alex decides to stay on Earth while Jamie boards a spacecraft capable of traveling at a significant fraction of the speed of light. According to Einstein's theory of relativity, time doesn't flow at the same rate for everyone. It depends on how fast you're moving. This means that as Jamie zooms through space at near light speed, time for Jamie slows down compared to Alex back on Earth. Here's where it gets fascinating. When Jamie returns to Earth after the journey, Jamie will have aged much less than Alex. For example, if Jamie's trip lasted 10 years from Alex's perspective on Earth, Jamie might only experience a few years passing due to the effects of time dilation. This isn't just a theoretical idea, it's been confirmed by experiments with atomic clocks on fast-moving airplanes and satellites, which show that time indeed passes more slowly for objects in motion. The twin paradox challenges our everyday understanding of time. It shows that time isn't absolute but relative, depending on your speed and gravitational environment. This phenomenon is a direct result of the speed of light being a universal constant. No matter how fast you're moving, light always travels at the same speed, and this unyielding rule reshapes how time and space behave at high velocities. But why does this happen? It all comes down to the Lorentz factor, a mathematical term that describes how time, length, and mass change as an object approaches the speed of light. The closer you get to light speed, the more pronounced these effects become. For Jamie, traveling at near light speed, time contracts, distances shrink, and even mass increases. These effects might sound like science fiction, but they're grounded in the very fabric of our universe. The twin paradox isn't just a fun thought experiment, it has real-world implications. For instance, astronauts on the International Space Station who orbit Earth at high speeds experience time slightly slower than people on the ground. Over long periods, these differences add up, though they're tiny compared to the dramatic effects seen in the twin paradox. Still, it's a reminder that the speed of light isn't just a number, it's a fundamental force that shapes the very nature of reality. With this in mind, let's explore another fascinating aspect of light speed, the Lorentz factor and how it quantifies these mind-bending effects. Now, let's take a closer look at the Lorentz factor, a key piece of the puzzle when it comes to understanding how the speed of light reshapes time and space. The Lorentz factor is a mathematical term that pops up in Einstein's theory of relativity, and it's what quantifies the strange effects we see when objects move at speeds close to the speed of light. Essentially, it tells us how much time slows down, distances shrink, and mass increases as an object accelerates. To break it down, the Lorentz factor depends on an object's velocity relative to the speed of light. The faster you go, the larger the Lorentz factor becomes and the more dramatic the effects. For example, if you're traveling at half the speed of light, the Lorentz factor is about 1.15. But if you crank that up to 99% of light speed, the Lorentz factor jumps to over 7. This means time for you would slow down to about 1/7 the rate of someone standing still, and distances in the direction you're moving would contract to 1/7 their original length. This isn't just theoretical, it's been confirmed by experiments. For instance, particles in particle accelerators, like those at CERN, reach speeds so close to light speed that their lifetimes appear much longer than they would at rest. This is because time dilation, as described by the Lorentz factor, stretches out their existence from our perspective. Similarly, the length contraction effect means that from the particle's point of view, the distance it travels through the accelerator is much shorter than it appears to us. The Lorentz factor also explains why nothing with mass can ever reach the speed of light. As an object accelerates, its mass increases according to the Lorentz factor, requiring more and more energy to keep pushing it faster. At light speed, the Lorentz factor would become infinite, meaning an infinite amount of energy would be needed, something that's impossible. So, the Lorentz factor isn't just a mathematical curiosity, it's a fundamental part of how our universe works at extreme speeds. It ties together the bizarre effects of time dilation, length contraction, and mass increase, showing just how deeply the speed of light is woven into the fabric of reality. With this in mind, let's move on to another groundbreaking experiment that helped shape our understanding of light and motion, the Michelson-Morley experiment. Now, let's step back in time to one of the most pivotal experiments in the history of physics, the Michelson-Morley experiment. Conducted in the late 19th century, this groundbreaking experiment aimed to detect the presence of something called the luminiferous ether. At the time, scientists believed that light waves needed a medium to travel through, much like sound waves need air. They called this hypothetical medium the ether, and it was thought to permeate all of space, providing a framework for light to propagate. The experiment was designed by Albert Michelson and Edward Morley, and it relied on an incredibly precise instrument called an interferometer. The idea was to measure the speed of light in different directions as Earth moved through the ether. If the ether existed, the speed of light should appear slightly faster when moving in the same direction as Earth's orbit and slightly slower when moving against it. This difference, known as the ether wind, would reveal the presence of the ether, but here's where things got interesting. No matter how many times Michelson and Morley ran their experiment, they found no evidence of the ether wind. The speed of light remained constant in every direction, defying the expectations of the time. This result was baffling and, frankly, a bit unsettling for the scientific community. It suggested that the ether didn't exist, and that light didn't need a medium to travel through space. The Michelson-Morley experiment's failure to detect the ether was a turning point in physics. It paved the way for Albert Einstein's theory of relativity, which completely redefined our understanding of space, time, and light. Einstein proposed that the speed of light is constant in a vacuum, regardless of the observer's motion, and that there's no need for an ether to explain how light travels. This idea became one of the cornerstones of modern physics. So, while the Michelson-Morley experiment didn't find what it was looking for, it ended up uncovering something far more profound: the realization that the universe doesn't operate the way we once thought. It challenged long-held beliefs and set the stage for the revolutionary ideas that would follow. With this in mind, let's turn our attention to another fascinating phenomenon that Einstein explored: the photoelectric effect, which further deepened our understanding of light's dual nature. Now, let's shift our focus to another groundbreaking discovery that reshaped our understanding of light: the photoelectric effect. This phenomenon, first observed in the late 19th century, occurs when light shines on a material and causes it to emit electrons. At the time, scientists were puzzled by how this worked. Classical physics suggested that light, as a wave, should transfer energy gradually, and the emission of electrons should depend on the intensity of the light. But experiments showed something entirely different. Even dim light could cause electrons to be emitted, as long as it was of a certain frequency. This was a mystery that couldn't be explained by the wave theory of light alone. Enter Albert Einstein. In 1905, the same year, he introduced his theory of special relativity. Einstein proposed a revolutionary explanation for the photoelectric effect. He suggested that light isn't just a wave, it also behaves as a stream of particles which he called quanta of light or photons. Each photon carries a specific amount of energy determined by its frequency. When a photon strikes an electron in a material, it can transfer its energy to the electron, knocking it free. If the photon's energy is too low, no electrons are emitted, no matter how intense the light. This idea was radical because it challenged the long-held belief that light was purely a wave. Einstein's explanation of the photoelectric effect was a game-changer. It not only solved the mystery of why certain frequencies of light could eject electrons, but also laid the foundation for quantum mechanics, a field that would revolutionize physics in the 20th century. For this work, Einstein was awarded the Nobel Prize in Physics in 1921. Interestingly, it wasn't for his more famous theory of relativity, but for his insights into the photoelectric effect, which highlighted the dual nature of light, both as a wave and as a particle. This discovery had profound implications. It showed that light could behave in ways that defied classical physics, opening the door to a deeper understanding of the universe at the smallest scales. The photoelectric effect also has practical applications today, from solar panels that convert sunlight into electricity to the sensors in digital cameras that capture images. So, while Einstein's work on the photoelectric effect might not be as widely known as his theories of relativity, it remains a cornerstone of modern physics, reminding us that light is far more complex and fascinating than it first appears. With this in mind, let's explore another intriguing aspect of light's behavior, the double-slit experiment, which further reveals its mysterious dual nature. Now, let's step into one of the most fascinating experiments in the history of physics, the double-slit experiment. This simple yet profound experiment reveals something extraordinary about the nature of light and, by extension, the universe itself. Imagine a barrier with two narrow slits and a beam of light shining through it. On the other side, there's a screen that captures where the light lands. If light were purely a wave, as classical physics once suggested, you'd expect to see a pattern of alternating bright and dark bands on the screen, known as an interference pattern. This happens because light waves passing through the two slits overlap and interfere with each other, creating areas where they reinforce or cancel each other out. And indeed, when the experiment is performed, that's exactly what we see, proof that light behaves like a wave. But here's where things get mind-bending. What if we send light through the slits one photon at a time? You'd think that each photon would pass through one slit or the other, creating two distinct bands on the screen. But that's not what happens. Over time, even single photons build up the same interference pattern, as if each photon is somehow passing through both slits at once and interfering with itself. This bizarre result suggests that light, and all particles for that matter, has a dual nature. It can behave as both a wave and a particle depending on how we observe it. The implications of this experiment are staggering. It challenges our everyday understanding of reality, showing that at the quantum level, particles don't behave in ways we can easily predict or visualize. The double-slit experiment also raises profound questions about the role of the observer. When scientists tried to measure which slit a photon went through, the interference pattern disappeared and the photons behaved like particles. This suggests that the act of observation itself can influence the outcome, a concept that continues to puzzle and inspire physicists to this day. This experiment isn't just a curiosity, it's a cornerstone of quantum mechanics, illustrating the strange and counterintuitive behavior of light and matter. It reminds us that the universe is far more complex and mysterious than it appears, and that light, with its dual nature, is at the heart of this mystery. So, as we continue to explore the extreme speeds and behaviors of light, let's keep in mind that even the simplest experiments can reveal the deepest truths about the cosmos. Next, we'll dive into another quantum phenomenon that pushes the boundaries of our understanding: quantum tunneling, where particles seem to defy the speed of light itself. Now, let's venture into one of the most mind-boggling phenomena in quantum physics: quantum tunneling. Imagine a particle like an electron approaching a barrier that, according to classical physics, it shouldn't be able to pass through. Think of it like trying to roll a ball up a hill so steep that it doesn't have enough energy to reach the top. In the classical world, the ball would simply roll back down. But in the quantum world, something extraordinary happens. The particle doesn't always bounce back. Instead, it can appear on the other side of the barrier as if it teleported through it. This is quantum tunneling. At first glance, this might seem impossible. How can a particle pass through a barrier it doesn't have the energy to overcome? The answer lies in the strange nature of quantum mechanics. Particles at the quantum level don't behave like solid objects. Instead, they exist as probability waves, which describe the likelihood of finding a particle in a particular place. These waves don't abruptly stop at a barrier. They extend into and even beyond it. There's a small but real chance that the particle will tunnel through the barrier and appear on the other side. It's not magic, it's math, and it's been experimentally verified countless times. But here's where things get even more intriguing. In some cases, quantum tunneling appears to happen faster than the speed of light. For example, experiments have shown that particles can tunnel through barriers in less time than it would take light to travel the same distance. This has led to debates about whether quantum tunneling violates the cosmic speed limit set by the speed of light. However, most physicists agree that it doesn't. While the tunneling effect might seem instantaneous, it doesn't involve the actual transfer of information faster than light. Instead, it's a result of the probabilistic nature of quantum mechanics, where particles don't follow the same rules as objects in our everyday experience. The implications of quantum tunneling are profound. It plays a crucial role in processes like nuclear fusion in stars, where protons tunnel through barriers to collide and release energy. It's also essential in modern technology, such as flash memory and scanning tunneling microscopes, which allow us to see and manipulate individual atoms. Without quantum tunneling, the universe as we know it wouldn't exist, and many of the technologies we rely on wouldn't work. So, while quantum tunneling might seem like a bizarre quirk of nature, it's a fundamental part of how the universe operates. It challenges our understanding of speed, energy, and even reality itself, reminding us that the quantum world is full of surprises. And as we continue to explore the mysteries of light and the cosmos, phenomena like quantum tunneling show us just how much we still have to learn. Next, we'll uncover another quantum marvel, the Casimir effect, where empty space itself exerts a force, and how it connects to the speed of light. Now, let's dive into another fascinating quantum phenomenon, the Casimir effect. Picture this: two uncharged metal plates placed incredibly close to each other in a vacuum. At first glance, you might think nothing would happen between them. After all, there's no charge, no obvious force at play. But in the quantum world, empty space is anything but empty. It's teeming with virtual particles that pop in and out of existence, a concept rooted in quantum field theory. These fleeting particles create fluctuations in the vacuum, and when two plates are brought close enough together, something remarkable occurs. The Casimir effect describes the force that arises between these plates due to the quantum fluctuations in the vacuum. Here's how it works. Between the plates, only certain wavelengths of these virtual particles can exist, while outside the plates, all wavelengths are possible. This imbalance creates a pressure difference pushing the plates together. It's a tiny force, but it's measurable and has been confirmed in numerous experiments. What's truly mind-blowing is that this force arises purely from the properties of empty space and the speed of light. You see, the Casimir effect is deeply tied to the speed of light because the virtual particles that cause it are governed by the same laws of quantum electrodynamics that describe how light behaves. The speed of light acts as a fundamental constant in these equations, shaping how these particles interact and how the force between the plates is calculated. Without the speed of light as a constant, the Casimir effect as we know it wouldn't exist. But why does this matter? Beyond being a curious quantum quirk, the Casimir effect has real-world applications. It's a key consideration in the design of nanoscale devices, where tiny forces can have a big impact. It also plays a role in theoretical physics, helping scientists explore the nature of vacuum energy and its implications for cosmology, including the mysterious dark energy driving the universe's expansion. The Casimir effect reminds us that even in what we perceive as empty space, the universe is alive with activity, governed by the interplay of quantum mechanics and the speed of light. It's a testament to how deeply interconnected these fundamental forces are, shaping everything from the tiniest particles to the vastness of the cosmos. Next, we'll explore another cornerstone of quantum mechanics, Heisenberg's uncertainty principle, and how it ties into our understanding of light and the universe. Now, let's shift our focus to one of the most intriguing principles in quantum mechanics, Heisenberg's uncertainty principle. This principle, formulated by physicist Werner Heisenberg, tells us that there's a fundamental limit to how precisely we can measure certain pairs of properties of a particle. Specifically, it states that the more accurately we know a particle's position, the less accurately we can know its momentum, and vice versa. This isn't due to limitations in our measuring tools, but is instead a fundamental property of nature itself. So, how does this connect to the speed of light? Well, the uncertainty principle is deeply rooted in the behavior of particles and waves, and light is no exception. When we measure light, we're often dealing with photons, the fundamental particles of light. These photons exhibit both wave-like and particle-like properties, a duality that's central to quantum mechanics. The uncertainty principle applies to photons just as it does to other particles, meaning we can't simultaneously know their exact position and momentum with perfect precision. This has profound implications for how we study light. For instance, when we try to measure the position of a photon with extreme accuracy, its momentum, and therefore its energy and wavelength becomes less certain. This uncertainty isn't just a theoretical quirk, it has real-world consequences. In experiments involving light, such as those using lasers or interferometers, the uncertainty principle sets a limit on how precise our measurements can be. It's a reminder that at the quantum level, the universe operates in ways that defy our everyday intuition. But the uncertainty principle doesn't just apply to light. It's a universal rule that governs all particles from electrons to quarks. It also plays a crucial role in the behavior of quantum systems, influencing phenomena like quantum tunneling and the stability of atoms. Without the uncertainty principle, the very fabric of matter as we know it would unravel. What's truly fascinating is how this principle ties back to the speed of light. The speed of light is a constant that underpins the equations of quantum mechanics, including those that describe the uncertainty principle. It acts as a kind of cosmic speed limit, influencing how particles interact and how information is transmitted. In a way, the uncertainty principle and the speed of light are two sides of the same coin, both shaping the rules of the quantum world. So, the next time you think about light, remember that it's not just a beam or a wave, it's a quantum entity governed by the same principles that make the universe so wonderfully unpredictable. And as we continue to explore the mysteries of light and quantum mechanics, the uncertainty principle reminds us that there's always more to discover, even in the things we think we understand. Up next, we'll delve into how the speed of light fits into the standard model of particle physics, the framework that describes the fundamental building blocks of the universe. Now, let's take a closer look at how the speed of light plays a pivotal role in the standard model of particle physics. The standard model is essentially the rulebook for how the universe's fundamental particles and forces interact, and the speed of light is one of its most critical constants. It's not just a number, it's a cornerstone that ties together the equations and principles that describe everything from the tiniest particles to the vastness of the cosmos. In the Standard Model, the speed of light appears in many of the fundamental equations, including those that describe electromagnetism, one of the four fundamental forces of nature. For example, Maxwell's equations, which govern how electric and magnetic fields behave, rely on the speed of light as a constant. This connection shows that light isn't just a phenomenon we observe, it's deeply woven into the fabric of the universe's laws. But the speed of light's importance doesn't stop there. It also plays a key role in Einstein's famous equation, E equals mc squared, which links energy and mass. This equation is a cornerstone of the Standard Model, helping us understand how particles gain mass through interactions with the Higgs field. Without the speed of light as a constant, this relationship wouldn't hold, and our understanding of particle physics would be fundamentally different. Another fascinating aspect is how the speed of light influences the behavior of particles at high energies. In particle accelerators like the Large Hadron Collider, scientists accelerate particles to speeds close to the speed of light to study their properties and interactions. These experiments rely on the fact that the speed of light is a universal limit, ensuring that the results are consistent and predictable. Without this constant, the very foundation of experimental particle physics would crumble. The speed of light also helps define the concept of causality in the Standard Model. Causality, or the idea that cause must precede effect, is a fundamental principle of physics. Because nothing can travel faster than light, the speed of light sets the ultimate limit for how quickly information or influence can propagate through the universe. This ensures that the laws of physics remain consistent and that the universe operates in a logical, predictable way. So, the next time you hear about the Standard Model, remember that the speed of light isn't just a number, it's a fundamental constant that shapes our understanding of the universe at its most basic level. From the equations that describe particles to the experiments that probe their secrets, the speed of light is a thread that runs through it all, connecting the dots in the grand tapestry of physics. Up next, we'll explore how the discovery of the Higgs boson, often called the God particle, relies on the speed of light to unlock the mysteries of mass and matter. Now, let's shift our focus to one of the most groundbreaking discoveries in modern physics, the Higgs boson, and how the speed of light played a crucial role in its detection. The Higgs boson, often referred to as the God particle, is a fundamental piece of the puzzle that explains why particles have mass. But uncovering this elusive particle required pushing the boundaries of what we know about speed and energy, and that's where the speed of light comes into play. At the Large Hadron Collider, or LHC, scientists accelerate protons to speeds incredibly close to the speed of light. These protons are then smashed together in high-energy collisions, creating conditions similar to those just moments after the Big Bang. The speed of light is the ultimate limit here. Nothing can go faster, so the protons are pushed to their maximum possible velocity. This immense speed is essential because it translates into the energy needed to produce the Higgs boson, which is a heavy and short-lived particle. The LHC's massive ring, spanning 27 kilometers, uses powerful magnetic fields to guide and accelerate the protons. As the protons zip around the collider at nearly the speed of light, they gain tremendous energy. When they collide, this energy is converted into mass thanks to Einstein's famous equation, E equals mc squared. Without the speed of light as a constant in this equation, the entire process would fall apart. It's this relationship between energy, mass, and the speed of light that makes the discovery of the Higgs boson possible. But why is the Higgs boson so important? Well, it's the particle associated with the Higgs field, an invisible energy field that permeates the entire universe. Just as swimmers moving through water experience resistance, particles moving through the Higgs field gain mass. The discovery of the Higgs boson confirmed the existence of this field, filling a critical gap in the standard model of particle physics. Without the speed of light enabling the high-energy collisions at the LHC, this discovery might still be a mystery. The speed of light also plays a role in how we detect the Higgs boson. When the particle is produced in a collision, it almost instantly decays into other particles. These decay products travel at or near the speed of light, and their paths are tracked by detectors surrounding the collision points. By analyzing these paths and the energy of the particles, scientists can reconstruct the presence of the Higgs boson. It's like piecing together a cosmic jigsaw puzzle with the speed of light as the guiding thread. So, the next time you hear about the Higgs boson, remember that its discovery was only possible because of the speed of light. From accelerating particles to detecting their decay, this universal constant is at the heart of one of the most significant scientific achievements of our time. Up next, we'll wrap up our journey through the universe's most extreme speeds of light by exploring how this constant continues to shape the future of physics and the mysteries it still holds. As we reach the final fact in our journey through the universe's most extreme speeds of light, it's worth reflecting on how this fundamental constant continues to shape the future of physics. The speed of light isn't just a number, it's a cornerstone of our understanding of the cosmos, and it holds the key to unlocking some of the greatest mysteries still out there. One of the most exciting areas where the speed of light plays a central role is in the search for a unified theory of physics. Right now, we have two incredibly successful frameworks, quantum mechanics and general relativity, but they don't quite fit together. Quantum mechanics governs the behavior of the very small, while general relativity explains the very large, like black holes and the expansion of the universe. The speed of light is a constant in both, but bridging the gap between these theories remains one of the biggest challenges in science. Could the speed of light hold clues to how these two worlds connect? That's a question physicists are actively exploring. Another frontier is the study of dark energy and dark matter, which together make up about 95% of the universe. We know they exist because of their effects on light and gravity, but we still don't fully understand what they are. The speed of light is crucial in measuring how dark energy accelerates the expansion of the universe and how dark matter bends light through gravitational lensing. Solving these mysteries could revolutionize our understanding of the cosmos, and the speed of light will undoubtedly play a starring role in that discovery. Then there's the tantalizing possibility of faster-than-light travel. While the speed of light is currently seen as an unbreakable limit, some theories, like the Alcubierre warp drive, suggest ways to bend spacetime itself, potentially allowing us to traverse vast distances without actually breaking the speed limit. These ideas are still in the realm of speculation, but they show how the speed of light continues to inspire bold new thinking about what's possible. And let's not forget the role of light in our search for extraterrestrial life. The speed of light defines the limits of how quickly we can communicate across the cosmos. If we ever detect a signal from another civilization, it will have traveled at the speed of light, possibly for thousands or even millions of years. This raises profound questions about how we might connect with other intelligent beings in a universe bound by this universal speed limit. So, as we wrap up our exploration of the speed of light, it's clear that this constant is far more than just a number. It's a guiding principle that shapes our understanding of space, time, and the very fabric of reality. From the smallest particles to the largest structures in the universe, the speed of light is at the heart of it all. And while we've come a long way in unraveling its mysteries, there's still so much more to discover. Who knows what groundbreaking revelations await us as we continue to probe the limits of light and the universe it illuminates. As we bring our journey through the universe's most extreme speeds of light to a close, it's incredible to reflect on just how much this single constant shapes our understanding of everything around us. From the way light travels through the vacuum of space to the mind-bending effects of time dilation, the speed of light is more than just a number. It's a fundamental thread woven into the fabric of reality itself. Over these 50 facts, we've explored how light defines the limits of our universe, from the smallest particles to the largest cosmic structures, and how it continues to challenge and inspire scientists to push the boundaries of what we know. We've seen how the speed of light is the ultimate speed limit, shaping everything from Einstein's theory of relativity to the way we measure the vast distances between stars. We've marveled at how light bends around black holes, how it carries the echoes of the Big Bang in the form of the cosmic microwave background, and how it might one day help us unlock the secrets of dark matter and dark energy. We've even ventured into the realm of science fiction, imagining what it might take to travel faster than light or communicate with civilizations light years away. But perhaps the most exciting part of all this is realizing how much we still have to learn. The speed of light isn't just a constant, it's a gateway to understanding the universe's deepest mysteries. It challenges us to think bigger, to question what we know, and to keep exploring the unknown. So, as we wrap up, here's a question to leave you with. What do you think the next great discovery about the speed of light will be? Will it help us unlock the secrets of quantum gravity, or will it reveal something entirely unexpected about the nature of reality? If you've enjoyed this deep dive into the universe's most extreme speeds, don't forget to hit that like button, subscribe for more cosmic explorations, and ring the notification bell so you never miss out on our next adventure into the mysteries of space. And let us know in the comments what fact about the speed of light blew your mind the most. Until next time, keep looking up and keep wondering about the incredible universe we call home.